When we go with chemical bonding, your chemical bonding chapter is basically divided into theories, or if I can say approaches, or if I can say theories. It is also divided, or it is also classified into a topic called concepts, small concepts. Your CBSE is trying to introduce you, or NCERT is trying to introduce small topics, so that further in your study, when you go for your master's degree or when you go for your master's, you have the basics in your 11th. And apart from these concepts, theories, concepts and everything, you have something called types, right? So when I speak about approaches theory or approaches of theory, in your syllabus you are going to learn about Coastal-Lewis theory, right? So Coastal-Lewis approach or Coastal-Lewis theory. You will also I'll be writing this theory and types again. Let me write types here. Apart from Coastal-Lewis theory, you are going to study MOT, molecular orbital theory. You will be studying about VBT, valence bond theory. You will be studying about Vesper, valence shell electron pair repulsion theory. Okay, you may also have this, not a problem. Valence shell electron pair repulsion theory, Vesper theory. You also have apart from these, like VBT is done, okay, this is linked to this is linked, right? When I come back to the concepts of chemical bonding, you have a concept of hydrogen bonding. You'll be studying the types of hydrogen bonding. You'll be studying what are the factors of hydrogen bonding. You'll also be learning how is hydrogen bonding formed. You'll also be studying whether because of the hydrogen bonding is the solubility increasing or decreasing, right? You'll also learn about our concepts of dipole moment. You will also be learning concepts of hybridizations, right? In hybridizations, you have Sp hybridization, Sp2, Sp3, Sp3, or Sp2D2, Sp3D2. Skip this. When you go to your grade 12, you also have inner D2, Sp2, D2, Sp3 hybrid orbitals. Apart from hybridization, you also have in your syllabus concepts like, small concepts like formal charges. Okay, this is again coming in between. Okay, you have concepts like formal charges. You'll be doing that. There is also a concept called Lewis dot structures. Unacademy, the biggest online platform, learning platform in India. Let's crack it. I'm Vani Potepalli, the verified educator for grade 12 students, CBSE, ICSE as well as state board students are with me. The upcoming classes which I'll be going to take are aldehydes, ketones and carboxylic acids. Along with that, solutions chapter would be done and a revision series on board examination and how to crack board 2021. I'm going to give you a clear analysis of the revision series. And in the special classes, I would be taking 3 sessions continuously. That is how to learn chemistry in Telugu. It will be on the respective dates. And I will also be taking a special class where you can plan it and you can just meet me on December 21st and 22nd. I'll be discussing what is the revision series, what is the revision strategy for board exam 2021. These are the Unacademy Plus subscription features where you have daily practice sessions, mock tests which are going on, live quizzes which will be going on, subjective test series coming soon. Join us. Unacademy iconic subscription features include personal mentors. You have live doubt clearing sessions. Weekly reports will be sent to the parents. Parent Connect, where the report will be sent to the parent and the educators are in contact with the parents too. A study planner is perfectly planned and all benefits of Plus also will come under iconic subscription. Revisathon, a revision marathon designed for science and maths learners for classes 10, 11 and 12. So students, it's a free session where with important concepts which will be covered. So you can identify your strength and improve the areas where you have to. So it's on 12th December for class 11th, 13th December for class 10 and 12. So timings would be 10:30 AM to 8 PM. So link is given in the description. Please enroll today. Remember the dates, 12th December for class 11th,
13th December for class 10 and 12th.
This is the class 11 subscription. Don't forget to use my referral code, that is Vani10 or Vani Life. This is the subscription rates you can go through. Grade 11th iconic subscription prices, that is again Vani10, Vani Life. Note my referral code. Next comes your grade 12 subscription, where prices are given. You have an option of 3 months and 6 months. Please try to use the code Vani10 or Vani Life to get the 10% discount. Then comes the grade 12 iconic subscription, 6 months, very less amount. So you can take that particular thing, use my referral code Vani10 and Vani Life. And most important thing, remember, if you want to enjoy all the free courses which I am going to conduct, you can use this referral code Vani10 or Vani Life to unlock that particular series, and you can enjoy the free special classes which are conducted with quality, quantity, and most important, it's going to give you a clear analysis of how to prepare for the upcoming board examinations. So don't forget students, Vani10 or Vani Life is my referral code, and don't forget to enroll into All India Unacademy Ascent competition on December 6th. Enroll today. Link is in the description. Right now, these are the basic concepts which I'll be covering. Apart from this topic, or apart from these concepts, your NCERT also gives you the information on types of bonds, right? So we very well know, we have studied in grade 12 also, ionic bond, covalent bond, coordinate covalent bond, coordinate covalent bond, or dative bond. This is also called as dative bond. So your whole chapter, I've just summarized it. They've divided into your theories, they've divided into your concepts, they've divided into types. Now I'll be going in detail about every concept of this, every theory of this, every detailing of this. But remember, whenever I'm doing, suppose I'm not going like, first page of NCERT, second page, no. I'll be going, suppose if I'm dealing with theories, I'll be dealing all the theories. If I'm dealing with concepts, I'll be dealing all the concepts. If I'm dealing with types of bonds, I'll be dealing all. What is the use of this? Because when a question paper is made, the particular chapter, every chapter has certain weightage. Based on that weightage, question will be given. And suppose this chapter, 1 mark question, 2 marks and 3 marks, in that way, 1, 2, 3 and 5. So this is the main concept. Please note it. I'll meet you again with the theories of chemical bonding. Yes, so we have already gone with the introduction of the chapter, that is chemical bonding. I'll be starting with the theories now. First I'll go in detail of all the theories, then come back to the concepts, then we'll be doing types of bonds. Right, now I'll be starting with the first type of theory, that is valence bond theory, or it is also called as orbital concept of bonding. So in short form, we call this theory as VBT. Right. So in this VBT theory, basically you have 3 subtopics. First would be the concept of hydrogen atom, where we're going to speak about the overlapping of orbitals. Then I'm going to also teach you about orbital overlapping. I'll also be teaching you about types of covalent bonds, that is sigma bond and pi bond, right? So first, when I'm speaking about the hydrogen concept, let us start. So basically, when I take an hydrogen, okay, I should state, I'm going to supply a certain amount of energy to this, almost 435.8 kilojoules per mole of energy is supplied to this. When I supply a certain amount of energy to this, immediately it will break up into hydrogen atom and hydrogen atom. Now I am labeling this hydrogen atom as HA, I will be labeling this as HB, right? So let us see. Now when this particular atom HA and HB is formed, how does this look? This is your HA atom, this is your HB atom, right? You have a nucleus in the center, here also you have a nucleus. And the electron of this, I am writing it here, EA. And the electron of this, I am writing it here, just for clarification. Like, you should have clarity while studying. Now, we very well know there are new attractive forces formed between this, isn't it? Okay, so I'll do that. Attractive forces. Fine. Now, Here these are already forces. You already have forces inside between the electron and the proton. Fine. Again you have new attractive forces formed between these two. Yes, and these are already old forces of attraction between them, right? So attractive forces new. These are also attractive forces, but they are between your old, because they are inside this. So old, new and new. When I go into the concept, EA and EB are having repulsive forces. Repulsive. HA and HB have again repulsive. Isn't it? Yes, because similar charges. So what type of forces are formed? We have attractive forces which have existed, and you have repulsive forces which also existed. What are they? When I start with attractive forces, what did I say? EA and HB. EA and HB. Attractive forces, correct. Now, next, what is the next attractive forces? EB and HA. Attractive. What are the repulsive forces? EA and EB. What are the second repulsive forces? HA and HB. Yes, this is what, right? Now, because of this formation of atoms once and because of the supply of amount of energy, immediately when two different atoms are formed, there are two forces which started acting. Already they have attractive forces among them, but once they have broken, a new attractive force has developed between EA of one, HB of the second one, EB of this, and HB or H of the second one. These are the new attractive forces, and as I said, repulsive forces between similar charges have also developed. So please note this. And now I am gradually going into the topic. These bonds have formed, fine, but when I go into the detailing of this particular concept, let us see. Graphically, when I represent this, how do I label this? Graphical representation of this. Okay, graphically I am representing the formation of hydrogen molecule. Now what happened initially? Now I am going to make a graph which shows the increasing values of potential energy, right? So let us see. Initially what happened, I'm taking this as the and here initially I had hydrogen atom HA here, and I have one more hydrogen atom HB. Now I have supplied certain amount of energy to this. Slowly the hydrogen atom has come closer, isn't it? Right? Slowly the hydrogen atom has come closer. And how does it look? So instead of this, I'm going to make this here and see. Initially I had hydrogen atom both individually, HA and HB. And from this, so plus and plus, I should not leave this, so plus and plus. From there, gradually that HA and HB, they started coming closer. They're trying to form a bond, right? So gradually HA and HB plus and plus. Now after that, slowly once they come and to particular point to some extent, right, they have still come closer, still almost, they're trying to form a bond HA and HB. Now at this particular point, right, when here they have completely formed or they have completely shared that electron pair and they have formed a covalent bond, and this center and this center of the nucleus. Now this particular point is called R0. What is R0? R0 is basically nothing, like, it is a bond length between H and HB. What is bond length? The internuclear distance between the centers of two nucleus. This R0 value is 74 picometer for hydrogen atom. Now what happens? Till now, attractive forces started acting. Attractive forces, but now when they have reached this point of R0, when a 74 picometer bond length has reached, and now what happens on this at this particular point, further if I am trying to get the particular atom closer and closer beyond R0, there is chance of bond cleavage, right? No, beyond this R0, if I am trying to still make it closer, more than the attractive forces, your repulsive forces starts taking charge. Your attract more than attraction, because repulsive, they're trying to now, the very closest they're trying to, they'll start breaking, and your repulsive forces. So till now attractive forces were dominating, but here at this particular point you have repulsive forces. So these repulsive forces will start dominating the part. And now suddenly what happens, your repulsive forces just started, and your concept of potential energy, see how much is the potential energy? Yeah, it is lowered. So first initially it will be very high, gradually lowered, and after some time the potential energy graph just zooms. Why? What is the reason for this? So initially what points I said? First, let me number this as 1, let me number this as 2, let me number this as 3, right? In 1, 2 and 3 stages, which forces dominated? Attractive forces. Attractive forces dominated. After that, when I came to number 4, at point 4, what happened? You have complete covalent bond formation, and a bond length of 74 picometer has formed between that. Then immediately your repulsive forces will come into picture. Your repulsive forces, because more than that it can't get closer, right? So at this particular point, first initially the potential energy forces, right? Our potential energy will be lower, and then it will just zoom up. Potential energy is lowered at this particular point. Fine. This is how the potential energy curve or graphs are shown for hydrogen atom, one after the other. So this, what is this trying to teach us? Basically this concept is trying to teach us how or what is the importance of bond length in any molecule, right? Now after this concept, now I have to show you how are these orbitals overlapping, right? How is this orbital, or what are the types of orbital overlapping apart from the basic hydrogen atom? So write the heading, types of orbital overlapping. So orbital overlapping concept. Orbital overlapping concept. This is what is the concept. Let me explain now. Fine. So when I speak about orbital overlapping concept, try to understand. Atomic, we already studied atomic orbitals combined together to form molecular orbitals. That is what we have studied. Fine. So in orbital overlapping concept, in your earlier chapters you've already studied types of orbitals. There is s orbital, p orbital, d and f. P orbital is again divided into px, py, pz, isn't it? Yes, fine. D is again divided into dxy, dyz, dzx, dx square y square and dz square. And F is all again divided into 7 subsections, right? So now when I am speaking about these orbital concepts, let me see how are they overlapping, because I already said they have to overlap, then finally atomic orbitals have to overlap, then finally form the molecular orbitals. So in this combination you have 3. First, positive overlapping orbitals, negative overlapping orbitals, and no overlapping orbitals. So to make it easy, free zone or no overlapping zone, I'll be showing that. Now, so in positive overlapping orbitals, now just see, suppose if I'm picking up a combination, now I have s orbital, p orbital, p, s, p, xy, xy, z, z. Now in positive overlapping orbital, suppose, let me pick up the basic thing. Now I'm drawing like this, right? Now I'm just making one line. Now I have, observe carefully, I am picking up one orbital like this. So I label this as PZ, okay, along the axis. Now I am going to pick up one more orbital and just overlap this. Okay, fine. So this also is PZ. So I am picking up PZ atomic orbital overlapping. Now this is minus, this is plus, this is minus. So what are overlapping? Positive and positive are overlapping, so it is positive overlapping orbitals. So both the signs positive. Now let us try with px and py. So what happens? Now suppose I'm taking the axis, I'm taking, now I took pz, let me come back, pick up y now, right? So y, as you know, your z, y and x, isn't it? X, y, z. Now I'm picking up this orbital, so I have to overlap both, so I'm getting them closer. So this particular overlap, 1, okay, so this should be one more overlap. So take your pen, just try to overlap it and see, right? Fine. So how should what symbol should I write? As I said, these are positive and positive, so this is positive, positive, negative, negative. So this is py overlapping. Now let me write for px and px, right? So let us write now px. Now this is your px, so px overlapping, and come closer, px and px overlapping. So just see, I've just drawn it here. So this is your plus, minus and minus, px overlapping, positive, right? So when I take further, now I'm going to px overlapping. Now I'll do with this on the sided, this also sided, this also sided. I have to overlap this and this combinations. So let me pick up one more example with px and s orbital, right? So now I'm just for an example, so I'm going to pick up one more px, right? Px and s, right? So s orbital is spherical and px is dumbbell shape. So x is this, right? So I have picked up x like this, px, right? So minus, plus, observe carefully, I am overlapping with an s orbital. Again, this also should be plus and plus, that is your this. Now ma'am, what is the use of positive overlapping? Whenever there is positive overlapping, observe carefully, you have attractive forces which are acting on them, right? Fine. So I'll go with the negative overlapping. I'll pick up the same. I'll pick up one example, right? Same, right? Draw. So when I'm again writing pz and pz. Now draw this lobe here, right? Now you have to overlap it. So take this and draw that dumbbell shape, right? When I speak about negative overlapping, observe carefully. What did I say? In positive overlapping, positive. Now here, your one positive, one negative. Again, this is positive, this is negative, this is negative, this is positive. So what happens? Two different lobes. Never get confused, ma'am, when the positive, negative, attractive. No, there are two different, node and antinode. It has become a node and antinode. So here, your repulsive forces start acting. Fine. So now if I draw with pz, just observe, draw with pz. Make one s orbital. If I write this is positive, this is negative, this is positive, so this is negative, right? So your repulsive forces start acting. So when I speak about no overlapping or zero overlapping, basically no overlapping or zero overlapping only happens when there is improper alignment. If the alignment of the lobes is not proper, see, this is proper alignment, this is proper alignment. If the alignment of the lobes is not proper, look here, one lobe is like this, and if one more lobe is coming in aligning like this, can you find any overlap in between these two? No. So because of the improper lobe or improper alignment, so I'll write this here, improper alignment of the lobes. Alignments means arrangement. Improper alignment of the lobes, there is no overlapping formed. So if you have like this, they will form attractive forces. If you have the sign, repulsive forces. When you have the orbitals, or when you have these orbitals in improper alignment, there is no overlap formation. Yes, so we'll come to the third topic of valence bond theory, that is VBT theory, that is types of covalent bond, right? So when I speak about types of covalent bond, just see, covalent bond basically are bonds, two types, right? Fine. First would be your sigma bond, second would be your pi bond. Fine. Okay, instead of this pi bond, I am writing the symbol pi bond. Let us be specific. Instead of the sigma bond, I am writing the symbol sigma. Now, ma'am, how is the sigma bond pi bond formed? Let us see. Now, I have already said p orbitals are px, py, pz. S orbital is spherical, s. Right? Fine. You also have d and also f. Now, in case of sigma bond, observe carefully. When a sigma bond has to form, how is the condition? How is this formed? Just observe. For a sigma bond to form, first important thing, the orbitals have to overlap axially along the internuclear distance. It has to, so they should be axial overlapping. Remember this. First, ma'am, what is this axial overlapping? Just see. Now let me pick up anything. You can pick up any axis and just see. Now this is your PZ. I'm going to pick up PZ. PZ orbital, dumbbell shape. Now I'm going to overlap this X. Okay, S basically first. So this is S. Now this E, are you not finding they are overlapping along the axis? This is called axial overlapping. Means along the axis, this particular axis they are overlapping and forming a bond called, just observe this shape, sigma bond. Right? Now let me pick up any, you can pick up any combinations. Now I picked up PZ and PZ. I will make it with PZ and PZ. This is also sigma bond. Axial overlapping. Are they not finding? You're finding this, right? Axially, right? So fine. So PZ and PZ also is sigma. PZ, PS also is sigma. Now PY and PY, is it sigma? Let us see whether it is sigma or not when I write this. Now pi bond is a type of bond where they are going to overlap, means the overlap, here it is along the axis, here they have to overlap up, above and below. So the overlap is above and below. Yeah, what do I mean by this? Now let me see. I have taken combinations of px and px, right? You can also pick up from px and px. You can also form between pz and pz. Now let's see. Here if I have like this, if I have like this, I have two more lobes here. I have one more lobe here. Now the bond formed above and below the bonds, right? Py, if I pick Py or Pz, okay, Py anything, not a problem because you can pick up the other side. The bond formed above and below the sigma bonds are called pi bonds. Above and below. Here it is axial in nature. Now when I speak about sigma bond, how are you finding? Where is the electron density concentrated? The electron density is concentrated along the axis. So isn't it stronger than pi bond? Yes, as you have seen, the whole electron cloud or electron density is concentrated here because it is tightly packed in the center. So electron density is concentrated along the axis. Done. Here, when I observe this particular bond, where is the electron density concentrated? It is above and below. Is it stronger than sigma bond? No, it isn't, because there is charge separation. There is separation of cloud above and below. So electron density is parallelly arranged or parallelly concentrated. It is concentrated above and it is concentrated below. I don't have it is equal, but it is above and below. Fine. Sigma bonds are stronger than pi bonds, right? Because it is axial, stronger than pi bonds, right? Because of parallel overlap, pi bonds are less stronger because we have to break and then only form pi bond. No, yes, whenever I say I have to form pi bond, I have to break the bond in between and then form pi bridges. That is what you have studied. So pi bonds are less stronger than sigma bond. Now let us see. When I speak about this particular example, What are you saying? The repulsion will be more in that, or repulsion will be more in that, or attraction will be more in this, or attraction will be more in that? This is more, no? Right? This is more attractive in nature. This is more, means compared to this, the distance is far. Here, this is sigma stronger, but here the repulsion is more. So know these points for sigma and pi bonds. You can pick up overlap. So your VBT theory explains about hydrogen atom. Your VBT theory explains about type of overlapping. It also explains about the differences between sigma bond and pi bond. Right. So we have already studied about valence bond theory. In valence bond theory, I have discussed about 3 important topics. Remember, because in your exam when they have asked you valence bond theory, they don't like summarize or something like that. You have to write about 3 important concepts. That is the formation of hydrogen atom with the information about repulsive forces and attractive forces. You will also be writing about orbital overlapping concept. Under that, you have positive overlapping, negative overlapping, as well as no overlapping zone, where alignment, if the alignment is not proper. After that, you will also be explaining the concept of sigma and pi bonds, where sigma bonds are more stronger than pi bonds. Right. Now I'll be coming to the next concept, next theory, that is Vesper theory. So as the name suggests, this is a shortcut. Let us write the full form. V stands for valence, S stands for valence shell, electron pair, R is repulsion theory, valence shell, electron pair, repulsion theory. So valence shell, electron pair, repulsion theory. As the name suggests, this basically explains about the repulsion or the concept of lone pair and bond pair. Right, let us see the postulates. It is basically very easy, but let us see. Whenever you are speaking about valence shell, remember one thing, Vesper means you have to speak in terms of 3 things. One is central atom, lone pair and bond pair. Right, in terms of these, your answer, your concept is clear. Now what is central atom? Basically, if I speak about, now I have an atom called, let's suppose I have carbon dioxide. In carbon dioxide, carbon is a central atom, carbon, central atom, right? This is your central atom. Apart from this, lone pair and bond pair I'll be representing. So that is your central atom around which your other atoms are linked. So according to valence shell electron pair repulsion theory, let us see the postulates or approaches towards that. First, what it says geometry of a molecule, geometry or shape of the molecule. So I need this whole board, geometry or shape. So geometry of the molecule depends on electron pair. Remember that it depends on electron pairs only. As I said just now, electron pairs are your lone pairs and bond pairs. Fine. Now your whole, this one, your central atom, I told just now, carbon dioxide, carbon is a central atom. In ammonia, nitrogen is a central atom. In PCl5, phosphorus is a central atom, right? In PCl3, phosphorus again is a central atom. The first element, remember, it is a central atom, right? So this molecular geometry, whether it is linear, planar, triangular, trigonal, planar, pyramidal, everything depends on electron pairs. So how many electron pairs do we have? So your electron pairs, as I said just now, electron pairs include lone pair is LP, bond pair is BP. Fine. Where are these present? Electron pairs are present around the central atom. So they are concentrated around the central atom. Done. Fine. Now always remember your lone pair repulsions are very, very stronger than lone pair, bond pair repulsions, which are stronger than bond pair repulsions. Remember, that means whenever in a molecule you have more number of lone pairs, those repulsions are more compared to lone pair means this will affect the molecule. So then compared to lone pair, bond pair, and compared to bond, means bond pair is safest. It will protect the molecule, giving it a proper geometry or shape. Right. Based on this, I'll write something else. Why am I doing this? Why am I writing? In the exam, start with geometry, link it with the electron pairs, then go to the order, then after that come back to the preferences. What happens? Now, if you have more number of bond pairs and bond pairs in the molecules, right? If that means bonded pairs are more, means all are linked. Look here, this is this 1 2 3 4 5 6, all are bond pairs, bonded. You have, suppose you have x1, x2, x3, x4, x5, x6, all are bonded pairs. I'm not finding any lone pairs, free electrons. So if I have such pairs, if bonded pairs are more, means if the particular molecule are listen, that particular molecule will have perfect geometry. You don't need to find perfect. It will possess a perfect geometry, perfect shape. Done. Suppose if you have lone pair and bond pairs in the particular molecule, both, right? Now problem starts. If lone pair and bond pairs are present, then it will give a distorted geometry. I'll show you with examples. It shows, or it gives you a distorted, means disturbed geometry. It will not exactly be linear. It will not exactly be octahedral. It will not exactly be trigonal planar. So it will show a variation in the bond angle. So lone pair, bond pair, geometry is distorted. So note these Vesper theory postulates. I'll come back and teach you the examples for them. Yes. So I've already given you the postulates for Vesper theory. I already said lone pair repulsion is more than lone pair, and bond pair repulsion will have the least, right? If the particular molecule has more of bond pairs, it is more stable and it has perfect geometry. Now we are going to discuss certain examples based on this concept. Now remember, so Vesper theory, basically I said I was speaking, the first word which I have given on Vesper theory was geometry, right? Shape of the molecule. Every molecule has a perfectly arranged geometry. You should practice that. You should know what type of geometry it has. So to learn the geometry, because this will be useful for your hybridization, to learn the geometry, there's a certain amount of general formulas which are given to us. So we'll be learning that, then going back to the geometry of the molecule. Now let us see. So basically the geometry of molecules, you have different categories. One is your linear shaped molecule, right? One is your trigonal planar, tetrahedral, trigonal bipyramidal, octahedral and pentagonal bipyramidal. Ma'am, first of all, whenever you're learning a new thing, remember, first learn the basic part, right? First of all, in such particular concepts, first what you do is take your book, first write all these names, 1, 2, 3, 4, 5, 6. Write all the names first. So write linear, trigonal, first learn the spellings and learn the name of that. Now once you learn the name of this, now let us write. First basically learn these structures and keep, because whatever example is given to you, you can directly write. This is called the basic template, the basic information for the shape of the molecules. So for linear 180 degrees, this is the shape. First practice the shape, and when I draw the structures, it's easy for you, right? For trigonal planar, now as the name suggests, tri, there are 3 atoms. This is your central atom. There are 3 other atoms surrounding the central atom, right? So trigonal in one plane, you are able to see I have only triangle formed in one plane. That's called trigonal planar. Right? Now when I speak about tetrahedral, 4 atoms, this is your central atom, 1 2 3 4, tetra, right? Central atom has 4 different atoms, but how many? There are 4 different sites arranged. So this is your tetrahedral arrangement. Be very careful, because initially you have to practice this. With this basic, I can write for any other example. Now when I speak about triangular bipyramidal, right, I'm only showing you 2-dimensional because I can't show you the other side of the board exactly. Now this is your pyramid formed, the same pyramid on the other side of the board. If I see this towards you, the central atom with 4, this is one angle forming 120 degree, and this is your 90 degree angle, and just a little bit down, and you have the trigonal pyramidal. And octahedral means in chemistry we speak octa means 6 here. 1 2 3 4 5 6, central atom with 6 atoms surrounded. This is a perfect geometry, 2 and above and here. After that you have pentagonal bipyramidal, again same bipyramidal, remember. So bipyramidal, one towards me and other towards the other side. Okay, yeah. You have equatorial and axial also. I'll teach you what is equatorial and axial. So these bonds, and these are the basic shapes which you have to remember. What you do, take your book, first draw, learn these spellings, draw this, and whichever example is given to you, you can easily write. Now when I have to take an example, suppose in the exam, your teacher has given you draw the structure of BeF2. So how am I going to apply Vesper theory in this? Just see. Now in BeF2, beryllium difluoride. Okay. Now easy. See here. This is your central atom. This is your central atom, and there are two bonds. Fine. What type are you finding? You've already studied this. This basic thing is easy to learn. 1, 2, 3, 4, 5 I've learned. Now an example is given to you. Your mom has given you this example. So see this. BeF2, just recollect. It comes under which one? First one, right? Central atom with two sides. So your idea already of drawing linear, you have that idea. So come back and draw that. So instead of A, you have BE. These two sides, F, this F. Done. So what is the angle for linear? 180 degree. Done. Easy. Let me come back. Now BF3. 3. Remember what did I say? 3 stands for this trigonal. Tri. So you already know this structure. So draw this. Instead of A, you have boron. 1, 2, 3. Draw it perfectly. Perfect geometry. You need to draw perfect geometry. Join this. We very well know trigonal planar has a bond angle of 120 degree. So draw this structure and make 120 degree. Done. Let me come back to CH4. Again CH4, when I speak about CH4, 4 is tetra, 3 is tri. So this has tetrahedral structure. 4 means tetrahedral structure. So you've already learned this structure. Draw that in this way. A, instead of A, your C. Hydrogen, 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 hydrogen. Draw that H above. 1, 2, 3. Here you have H. Here and here. Again H and H. This is your CH4 molecule. So join all. 1, 2, 3 and tetrahedral structure. What? So how did I know this? I have done this, right? I have taken, remember this, 4 means tetra, so I have drawn the tetrahedral. Now this is easy. PCl 5, as I said, 5 means, I already said, central atom with trigonal pyramidal. It will be in this, the 5th one will go into the board. Yes, right. Now let us draw this. So phosphorus is the central atom. You can draw with PCl for anything. So draw these bonds. 1, 2. I have how many? 5 more. 3, 4, 5. F, 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 F and F. Done, because it is trigonal, coming under trigonal pyramidal, and the bond angle 90 degree and the bond angle 120 degree here. Let us come back and do this. SF6. In chemistry I said 6 means octa. Yes, octahedral structure. Draw S here. All the 6 bonds. 1, 2, 3, 4, 5, 6. F, F and SF6 all together. 90 degree, as we said, 90, 90. So how did I do? I took, first I learned all these structures which are standard, and your teacher has given you these examples, and seeing this formula, 2 means linear, 3 means tri, 4 means tetra, 5 means trigonal bipyramidal, 6 means octahedral. You did the examples, you already learned the bond angles, apply in that. Yes, let us come back and do some more examples for this. Right. So I've already discussed about the postulates for Valence theory, or Vesper theory, that is valential electron pair repulsion theory. I've also asked you to learn the structures of linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. If you learn these 5 or 6, it's easy for you, whichever example is given. So let us go with the second set. So what is the difference between the earlier table and this one? In the earlier table, I've given you examples for the molecules having no lone pairs. There were no lone pairs around them. It is only the basic central atom and the surrounding ligands around that, the surrounding atoms rather. Okay. So now I'm giving you examples for the atom or the molecules having lone pairs, right? Those were without lone pairs. These are with lone pairs and bond pairs, right? Let us see. Now there is Now this is the basic standard formula. So let us see how to use this particular data. These you already memorized these, right? 1, 2, 3, 4, 5. You already have that in your mind. Now let us see. Now here A is the central atom, B is the surrounding atom, and L stands for the lone pair of electrons, right? So when I speak about lone pair of electrons here, now see, as soon as this molecule is given to you, okay, now this is given to you, how to write this? Now come here, just count. This is 2 plus 1, 3, right? 2, 3, 4. Okay, total are 4. Again 2, 3, 4. But there is one lone pair here. So what is the structure which has this 4 atoms? Let us see 4. How many? There are total should be 4. Now this is how many? 3, isn't it? Now this is how many? 1, 2, 3, 4. 4. So this structure resembles this. Can I take this? Let me see. 1, 2, 3, 4, 5. No, this is not the structure. A, B to L is this structure because total number of 4. Now let me write this in this form. Okay, trigonal planar form. So how is this looking? I have to also show lone pair of electrons. Write exactly the same shape. So I'll use this pen. Exactly the same shape. This is A. Done. Now how many B2s? Write these B and B. Done. So there is one more bond I have to show. That is your lone pair. Draw one line like this. Show this lone pair. This is your structure. Right. So this is your AB2L structure with one lone pair. So how many lone pairs and how many bond pairs? Bond pairs are 2. LP is 1. Done. Let us come back and draw. Now you have A, B to L. Now count 2, 3, 4. Fine. So which is that structure here? 2, 3, 4. Here also 2, 3, 4. Both are same, right? So let us not take this. Let us come back to this. 2, 3, 4, 5. Total of 5. Bond pairs are also there. Lone pairs also. The total 5 I have to search. Now this is how many? 1, 2, 3, 4. No. Let us come back. 1, 2, 3, 4, 5. Yes, this structure was trigonal planar structure. This structure is tetrahedral structure. Now how did I know this? I have counted the bond pairs and lone pairs. Fine. Now let us write. Now write A in the center. Fine. This is done. Now you have 2 bond pairs. Start from here. This is bond pair. This is also bond pair. Draw one bond pair. B. Draw one bond pair. Okay. This and this. How many are left out? This and this. This is your lone pair. Now this also is your lone pair. Yes, have you seen? So this is your tetrahedral structure. Let us write. BPs are how many? 1 and 2. How many LPs are there? 2. Simple. Let us write this. Now count. As soon as the example is given, just count. 4, 5, 6. Okay, 6. Is this 6? No, this is 3. Is this 6? No, this is 4. Is this 6? No, this is 5. Let us count whether there's 6. 1, 2, 3, 4, 5, 6. Yes. So I have to make a structure with one lone pair with 6 atoms. So this is the thing. So take that. Draw A. Yes, done. Now how many lone pairs should I show? Only one, right? So just take this as a lone pair. Remaining all you can show as B. This is B. One more B. One more atom. This also is an atom. Pick up lone pair. Yes. So remember, these bonds, whatever are there along this, are called axial bonds. I am writing something here. This and this are called axial bonds. Axial bonds are always longer. This is E, this is E, this is E. These are called equatorial bonds. Equatorial bonds, which are shorter. Okay. Yes. There are more repulsive forces on the axial bonds than equatorial bonds. Remember, because they are along the axis. Equatorial bonds are spaced, they are open and they're spaced. So they are less repulsive forces. Less. So in this particular example, how many bond pairs and how many lone pairs? Bond pairs are 1, 2, 3, 4. BP are 4. How many lone pairs? L is 1. So this example, let me count. 3, 4, 5, 6. Which is the example with 6 which you've already studied? This one. Let us see if it is correct. 1, 6 plus 7. Okay. Let me come back and see how many does this have? 3 on this side, 3, 6. So you will be writing an example with this. Let me count this. 1, 2, 3, 4, 5, 6. Again, you will draw the structure with this. So what did I do? After writing, you will write number of lone pairs and bond pairs. Now I have given you a list of examples here. Just count, just see how many are there. Now suppose if I take this example, XCF2. How many are there? 2 plus 1, 3. Linear structure. Let me come back and see. 3 plus 1, 4. Which is that 4? 1, 2, 3, 4. This is the structure. SF6. 6 plus 1, 7. Which is that structure? The structure. Octahedral. Water molecule. 2 plus 1, 3. The structure. But you will get in a bent form. Ammonia. 3 plus 1, 4. So what is the use? Learn this basic thing, then start applying whichever example is given to you. So for that, try to practice all these examples. So once you learn all these, whichever example your teacher gives you, you can directly write in that structure. This is your Vesper theory. Right. So I've already started with the concepts. The first theory which I taught you was valence bond theory, that is VBT. After that, I've taught you a theory called Vesper theory, valence shell electron pair repulsion theory. And now the third theory which I'm going to teach you is MOT. MOT, that is molecular orbital theory. So molecular orbital theory was invented by Fund and Millikan. Right. So let us come back. In molecular orbital theory, basically, when I said valence bond theory, I was explaining about overlapping of orbitals, right? When I thought about Vesper theory, I was teaching about electron pairs, lone pair, bond pair, bond pair, bond pair. Now, when I am teaching about molecular orbital theory, or when you are learning, remember in your mind, you have to concentrate on atomic orbitals and molecular orbitals, right? Right. So, MOT, again, you can also call as LCAO. LCAO means linear combination of atomic orbitals. This is also the name given for MOT theory. All are same. Let us learn. So in MOT theory, according to the postulates, let us first learn the postulates and then go back to the concept. In the postulates, first important thing, what does this say? Yeah. Now, as the name suggests, molecular orbitals. So start your concept with molecules. So in molecules, right? Fine. Remember this. I'll try to use this later. In molecules, electrons are present in molecular orbits. Remember this. I'll explain later. Now, how are molecular orbitals formed? Atomic orbitals combine together to form molecular orbitals. That is what you have studied. Atomic orbitals combine to form molecular orbitals. Yes. So form molecular orbitals. Done. Now how many atomic orbitals? How many ever atomics? About 2 atomic orbitals combine to form, you will get 2 molecular orbitals. So the number of atomic orbitals overlapping will be equal to the number of molecular orbitals. So number of atomic orbitals will be equal to overlapping will be equal to number of molecular orbitals formed. How many ever combine, so many molecular orbitals will form. Right. So whatever, like, you know, when I'm trying to explain the function of atomic orbitals, we use a term called psi, right? Quantum physics, you use the term psi for explaining the atomic orbitals. This psi is a wave function, right? When I'm using a new term, and let me explain this again. Basically, molecular orbitals are of 2 two types. I already said atomic orbitals combine to form molecular orbitals. Now in that again, yes, you have bonding molecular orbitals, BMO. So BMO is called bonding molecular orbital. There is one more type of molecular orbital called ABMO. ABMO means anti-bonding molecular orbital. Anti-bonding molecular orbital. Yes, fine. Next important thing. I am taking this function to explain this concept. Just see. Suppose I have an atomic orbital A. This atomic orbital is going to combine with one more atomic orbital B. This is going to form plus or minus, right, a molecular orbital AB. Fine. Suppose if I have a condition, right, if I have a condition, suppose I'm going to take both like separately. Suppose if I have psi A plus psi B, I get bonding molecular orbital. Suppose if I take psi A minus psi B, I get anti-bonding molecular orbital. Remember that. Yes. So I'm going to use all these terms when I'm doing the molecular orbital structure. Remember that carefully. Addition will give you bonding. Subtraction will give you anti-bonding molecular orbital. So I'll meet you with an example in my next session. Yes. So I already taught you the postulates for molecular orbital theory, but now when before going to the concept of molecular or filling of orbitals, so let me teach you important thing. Whenever you're filling molecular orbitals, alright, sorry, if you're filling atomic orbitals, they are going to follow, I should not say molecular, atomic orbitals combined to form molecular. They are going to follow Aufbau principle. Remember this. What is Aufbau principle? You are going to fill the orbitals according to the energy levels. 1s is filled, then 1s, then 2s, then 2p, like that. So you will be filling the electrons according to the Aufbau principle, starting from the lowest energy to the highest energy. So lowest energy to highest energy, right? You will be filling that according to the sequence. We'll do that with an example. Next, it's this filling, orbital filling also will follow a principle called Paulie's exclusion principle. Paulie's principle. What is Paulie's principle? It says that whenever you're filling an atomic orbital, only the opposite spin electrons are paired up. So according to Paulie's, opposite spin electrons are paired up. Only opposite spin are paired up. You should not write like this, wrong. Opposite spins only will pair up. Your orbital filling also will depend on Hund's rule. Hund's rule or Hund's principle. What is Hund's rule? Let us see. Suppose if I have an orbital like this, okay? Yes. So how do you fill? Now suppose this is 2s, this is 2p, right? Now this is your 1s. I have an configuration 1s2, 2s2, 2p, 4. This is some element. Okay, which element is this? 4, 5, 6, 7, 8, oxygen, right? How should I fill? According to Hund's rule, orbitals are half filled and then full filled. Half filled and then full filled. According to Hund's rule, orbitals are half filled, 2p4, right? 1, 2, 3, 4, then full filled. You should never fill full and then go back. No, it should be half filled and then come back and fill the next electron. So your MOT theory is going to follow Aufbau principle. It will follow Paulie's principle. It also follow Hund's rule. So based on this, I will start. Now, when I speak about MOT theory, how am I going to apply this? So now I already said bonding orbital psi b is equal to psi a plus psi b. Anti-bonding molecular orbital is equal to psi a minus psi b. Wave function. Yes. How am I going to show this in terms of example? Understand, I'll give you a clue. For atomic numbers, careful, atomic numbers 1 to 7. So what are the elements from 1 to 7? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. So oxygen is 8. I should not write it. Till all these elements will follow one sequence, and 8 and above, greater than 8, will follow, that is from oxygen further, this in fluorine, neon will follow one sequence. Okay, now let us see. So for elements from 1 to 7, how should I write? Okay, I'll use this down and I'll write that above. So elements above 8. For example, starting from oxygen, let us see. So now I'm going to write the filling. How am I going to fill the electron into the orbitals? You have to follow a sequence for that. Now let us see. I said you have to follow Aufbau principle, you have to follow Paulie's and Hunt's. I'm following Aufbau now. According to this, suppose if I pick up an element nitrogen, I'm going to write this nitrogen here. Or first let me write the general form, then I go back. So general form, let us start. I'm following Aufbau principle. Start from the lowest energy level, that is 1s. 1s is what is the shape of s orbital, or what type of overlapping? Sigma overlapping, right? So start from 1s, sigma 1s. Immediately after this bonding, anti-bonding will follow. Yes, so this anti-bonding will represent as sigma star 1s, right? After 1s, it will be followed by 2s. This will be followed by sigma star 2s. Right? Fine. After sigma, 1s is over, 2s is over. Now I have to start with 2p, isn't it? So you start with 2p. So s orbital always is 2 electrons. 1s2, 2s2, 2s2, 2. Only, it will fill only 2 electrons. After this is 2p. Yes. So this particular element till nitrogen, you have to write like this. S, bonding, anti-bonding, bonding, anti-bonding, and now let us come back. Now start with 2py, okay, which is degenerate means equal in energy, with 2py equal to 2p. So x and y, right? Both z is axis is sigma, x and y equal, and the next one which is less than z, because 2pz is x axis, sigma 2pz. So the order is x, y, z. Then comes back, it will become anti-bonding pi to px, anti-bonding pi to py, less than anti-bonding pi, so sigma, no? So sigma anti-bonding 2pz. This is your sequence. But now when I am coming above oxygen, I have to be careful. So write same, first one is same, second is same, third is same, fourth also is same. But when you are coming to pi, remember, because here from oxygen double bond starts, your sigma 2pz will come first. Sigma 2pz, less energy, then comes sigma 2px equal sigma 2py equal. So your sequence is zxy. Remember that. This is the only difference. Zxy in the antibonding orbital. So note this. We'll be doing an example. Yes. So I've already taught you how to fill the electrons, or how to fill from the lower energy to the higher energy. Let us remember one logic. Till nitrogen, the filling is sigma 1s, sigma along with the anti-bonding also, that is sigma star 1s. So it is 2, 2, sigma 2s2, sigma star 2s2, right? Now, this is, remember one sequence, till nitrogen, that is 1 to 7, it is XYZ filling, XYZ anti-bonding filling. Remember, here it is bonding, this is anti-bonding filling. But when it comes from oxygen, that is above 7, your filling should be ZXY, XYZ. Remember this, it is easy for us to write. If this is the logic. ZXY is for bonding, BMO, this is ABMO. Right, now let us write. Now what did I say? Sigma and sigma star. Now I have to start with pi. X and y are pi, z is sigma. So write pi 2px equal energy with 2 pi, all are 2, right? Pi 2py. Then what should I write? Then sigma 2pz. After this, after filling bonding, then I have to come, because bonding will follow by antibonding, bonding, antibonding. The bonding is over. Now I have to write. Now what sequence did I follow? X, Y, Z. Now again you follow X, Y, Z. Pi star 2px square equal to pi star 2py sigma star 2pz. This is a sequence, right? Now let us write for oxygen. I am using the same sequence. Let us write for oxygen. First of all, let us write the general formula. I'll use this. I am writing the general formula. Sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2. After sigma, I have to write this bonding. Z is always sigma, sigma 2pz. This is 2. Pi 2px equal to pi 2py, equal energy, degenerate orbitals. After zxy, I have to write bonding is over, antibonding. This is x, no? X is always pi, pi 2px star, which is degenerate with pi star 2py. Finally, you have z, that is sigma 2pz star. If you remember the sequence, let your teacher give you any example, it is easy for you. So now let me write for nitrogen. So for nitrogen, let me erase this and come back with the original example. For nitrogen, as soon as this element is given, write the atomic number. Atomic number 7. So for 2 nitrogens, total are 14 electrons I have to fill. Now start writing the filling of electrons. Start. Sigma 1s2. Out of 14, 2 are over. Sigma star 1s2. Sigma 2s2. Sigma star 2s2. 2, 4, 6, 8 are over. What did I say? Follow this sequence. After S, you have to go to X. Pi 2 p x 2 is equal to pi 2 p y 2. Yes, over. Now count. 2, 4, 6, 8, 10, 11, 12. Only 2 are there. What should I write? Z. Sigma 2p z2. Should I write anti-bonding electrons? No. Why? Already we have only 14 electrons and I have already filled 2, 4, 6, 8, 10, 12, 14. No anti-bonding orbitals here. So start filling this here. So for funness, first draw one orbital. One more atomic orbital. You are going to make lines like this. Just join. For bonding molecular orbital at the lower energy, for anti-bonding molecular orbital for higher energy. This is 1s, this is 1s. How many do I have here? Half, half, full. This is BMO, this is ABMO. Now, there are 2 and 2, 4. Bonding also I have 2. Anti-bonding also I have 2. 1s is over. Let us write for 2s. Pick up. This is 2s. This is also 2s. Draw both the orbitals. Make one line. Just draw bonding or molecular orbital here. And draw anti-bonding molecular orbital here. In 2s2, 2 and 2. 2 and 2. Both are filled. Bonding is filled, anti-bonding is filled. Come back to P now. P, as we know, 3, 1, 2, 3 on both the sides. P on both the sides. Now take this, make orbitals. Now let us see how to draw here. Now this is 2p. This is 2p. How many are there in 2p? 1, 2, 4, 6. Right? So according to this configuration, 1s2, 2s2, 2p3. Correct, right? So there are 6. 3 here, 3 here. Yes, so 1, 2, 3. Fine. So here you're going to write 1, 2, 3. Now, according to this particular thing, do we have any anti-bonding orbitals? How did I write 6? Just see, 3 for 1 nitrogen, 3 for 1 more nitrogen. So start filling. Basically, what do you have now? 2p x and y. This is pi 2p x, pi 2p y. 1, 2, 3, 4. Above that, you have 2px sigma. Join this. Sigma 2px. Do you have anything above? Normally what do you get? Bonding and anti-bonding you have to write, right? Now xyz. After that again you have xyz. This is anti-bonding. No, nothing is there. I have not written because already 2, 4, 6, 8, 9, 10, 11, 12, 13, 14 are over. I should not write anything in anti-bonding. This also empty. This is how you represent. But now I have to calculate the bond order. What is bond order? Bonding orbital. NB minus NA by 2. Number of bonding orbitals minus number of anti-bonding orbitals by 2. Count the number of bonding orbitals. 2. These are all bonding. The base ones are bonding. 2, 4, 5, 6, 7, 8, 9, 10. Again 1, 2, 4, 5, 6, 7, 8, 9, 10. 10 minus anti-bonding 2, 4. Do I have anything here? Anything? No anti-bonding. So 4. 6 by 2, 3. That is the reason nitrogen has triple bond always. What is bond order? The number of bonds around the atom. I got 3. That means my thing is correct. So let us write with oxygen. Yes, so we have done for nitrogen. Let us do for oxygen. Observe carefully. As soon as this element is given to you, write the atomic number. Atomic number 8. So for 2 oxygens, total number of electrons are 16. Right? Let us write 1s2, 2s2, 2p. If I write 4, 4, 5, 6, 7, 8, this is wrong. Okay, 4 correct. Yes, 2p4. So 4, 8 electrons here. And again for one more, 1s2, 2s2, 2p4. Now let us write the orbital filling. So I have to follow that sequence. Sigma 1s2. Basic Abbo principle. Sigma star 1s2. Sigma 2s2. Sigma star 2s2. Correct? I have to fill total 16 electrons. After S, what should I follow? This sequence. Z is always sigma 2p Z. It can fill only 2 electrons. 2. X is always pi 2p x2, which is equal to pi 2p y2. Let me see, because I should not fill more than 16 electrons. 2, 4, 6, 8, 10, 12, 14. I have 2 more electrons to fill. So write this because these are all degenerate. So Z is over, X is over, this also is over. These 3 are over. Now I have to come to this. 2p x, no? So pi star. Bonding is over. 2px. Ma'am, should I write 2 here? No, you should not write. Because according to Hund's rule, half filled then full filled, which is equal to 2py anti-bonding 1 and 1. Now count 2, 4, 6, 8, 10, 12, 14, 15, 16. Correct? Now start drawing. For 1s, this is 1s. Fill the electrons, bonding. 1s is here, 1s is here, full filled, fully filled, fully filled, fully filled, BMO, ABMO. Now I have to write for 2s. Make 2s on this side, make 2 atomic orbital 2s on this side. Join both the atomic orbitals and try to form a molecular orbital. Molecular orbital. 2s and 2s2, 2 plus 2, 4. 1, 2, 3, 4. Both the electrons are filled. BMO, ABMO. Now I have to draw for, this is also done, I have to draw for 2pz. First make 3. Here also try to make 3. Now this is 2p, this is also 2p. Now observe carefully. According to this configuration, 1s2, 1s2. This is 2p4 means how do you write? Write like this. 1 half, half and 4. Correct? This is also same. 1, 2, 3 and 4. I filled it correctly according to Hund's rule. Half filled, full filled. Why did I write this one? Because according to the configuration it is 2p4. 4, 5, 6, 7, 8. Half, 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 1. Now draw. How do I get? What did I get now? At the base I have got 2px. Sigma 2pz 2. After that I've got pi p. How many do I have? 2 and 2. After this I have got 2px x, right? Anti-bonding. This is anti-bonding. This is ABMO. How many do I have? I have only 1 and 1. Do I have anything in 2px, sigma, 2pz, anti-bonding? Nothing. Join this. Now, I have done everything. Let me count. 2, 2, 2, anti-bonding 2, 2, sigma 2, anti-bonding 2, z 2, sig x and y 2, 2, anti-bonding x 1, anti-bonding y 1. Now I have to calculate bond order. Bond order is equal to bonding minus anti-bonding by 2. So how many bonding do we have? 2, 4, 5, 6, 7, 8, 9, 10. How many anti-bonding we have? 2, 4, 5, 6 divided by 2. 4 by 2 is 2. That is why oxygen has double bond. Yes students, welcome back. We have already started with the chapter and we have done valence bond theory. We have also done molecular orbital theory. Then gradually I also completed valential electron pair repulsion theory, that is Vesper theory. So after that let us go to one more theory, that is Cousel-Lewis approach for chemical bonding. So write the heading Cousel theory. Cousel-Lewis approach. So basically when I speak about Cousel-Lewis approach, it's nothing, it's simple basic theory. What it suggests, every element, basically suppose if I take a basic element hydrogen, or if I take the next element helium, okay, next lithium. So every element tries to either share its electrons or transfer its electrons with some other atom and finally form a molecule. So during this process what is happening? It's trying to attain a certain amount of stability in the molecule, right? If there is stability, only the molecule tries to exist, isn't it? So this particular concept of attaining stability was explained by Cousel and Lewis. So they have framed a rule called Octet Rule. Remember, Cousel and Lewis, they framed a rule called Octet Rule. It is basic thumb rule in chemistry, where let us see what does it suggest. So concept is attaining stability either by transferring or either by sharing of electrons. So let us write Octet Rule. So when I speak about Octet Rule, as the name suggests, octet means 8. Right? It can be duplet also for attaining stability, like helium. Octet means attaining the valence electrons of 8 in the valence shell. So let us write the rule. So what does it state? Every atom of an element, every atom of an element, what do you say? It has to participate, right, in a particular chemical bonding. Every atom of an element enters into chemical combination either by transfer or by sharing of electrons to attain, remember our final concept is it has to attain a stable configuration, to attain a stable octet or 8 electrons in valence shell. Okay, I have written a lot of things here in their valence shell. This is your octet rule. Let us read again. Every atom of an element, right, particularly atoms of individual elements, atoms combine to form molecules, that is what you have studied. Atom of an element, they enter into a chemical combination, they're going to join or form a bond either by transfer, they're going to transfer the electrons, or they mutually share between both of them. Till what extent? Till they attain a stable 8 electrons in their valence, or they are going to attain a stable octet configuration in their valence shell. That is what is the octet rule. So using this octet rule, Lewis has designed, or he has tabulated Lewis dot structures, which we will be studying gradually. I will be teaching Lewis dot structures for monoatomic atoms and Lewis dot structures for polyatomic atoms also. So what is monoatomic? Mono is basically one atom, right? Now lithium, hydrogen, like that, one atoms. If I say polyatomic atoms, it can be more than 2, right? Water molecule, carbon dioxide molecule, ammonia molecule, sulfur dioxide. Isn't it more than 2? Sulfur dioxide, you have 1 sulfur, 2 oxygens. Ammonia molecule, 1 nitrogen, 3 hydrogens. So we'll be doing Lewis dot structures for such elements. So note this. Yes, so now we'll be writing Lewis dot structures basically for all the elements. Let us start with Lewis dot for dot structures. So Lewis dot structures, now I'm going to pick up monoatomic elements side. So first you are going to write the name of the element. Write the name of the element, fine. Write the atomic or write the electronic configuration. After that, write the Lewis dot structure. Lewis dot, after writing the Lewis dot and Lewis representation also, so I'll put it as Lewis representation, then write the valency. So your answer is complete. So when I pick, now I'm going to pick up monoatomic atoms. So suppose if I pick up the basic element, lithium, okay, lithium atomic number, it is 3, so electronic configuration 2 and 1, correct? So let us write this in the form of Lewis dot. Write lithium L capital, small I. So this is your stable configuration, don't worry. This is where you write the valence electron. So the outermost or the valence shell represents the valence electron. So in this particular lithium, how many valence electrons you have? 1. So what is a valency? That means, what is valency? The number of combining capacity. That means by donating this 1 electron, it becomes stable. So how many can it donate? How many ever it can donate? That is called valency, the combining capacity of the element. So it can donate 1. So the valency is 1. Let us write for lithium, beryllium. Atomic number 4, 2, 2. So beryllium, I'm picking up. Now write the configuration, dot 1 and 2. So the valency 2 is stable, it can donate 2. Boron, 5, 2, 3. So boron, I'm writing here. Now this is stable, 3 valence electrons, 1, 2, 3. Fine. Yeah, so the valency, it can donate 3 electrons or and form stable configuration. Now when I'm going back to one more, lithium, beryllium, boron, carbon. Atomic number 6, 2 and 4. Now take your carbon atom, start filling the electrons. I try to make one, then we'll pair it up. 1, 2, 3, 4. That's why carbon is tetravalent. So what is the valency? It can donate 4, right? Means it can share 4, and with the stable configuration, so valency is 4. Let me write next. So lithium, beryllium, boron, carbon, nitrogen, atomic number 7. So 2 and 5. So how many are there now? 5. Now careful. So from here, from atomic number 7, so a little bit careful while writing the configuration. Now this is 2, stable. I have to show 5. Now fill. 1, 2, 3, 4. And the 5th one, pair it up. right? So this is 5. Now understand carefully, what is the difference between this and this? Here there are 4 electrons, so the valency is 4, but from 5, 6, 7, 8 it has become, losing 5 is very difficult. Instead of that, accepting 3 electrons, because 8 is octet, 8 minus 5 is 3, so accepting 3 electrons is easy, isn't it? So from now 5, the valency here become 3, because valency is 3, because 8 minus 5 is 3. This is easy, right? Accepting 3 is easy, then donating 5. Now nitrogen, oxygen, atomic number 8, 2 and 6. So now write oxygen element. Now let us start with single, no problem. 1, 2, 3, 4, 5, 6. Right now here you have 2 pairs, isn't it? So try, you can make and take it and just pair it up as this, not a problem. That's also correct. Now I already said instead of donating 6, it is easy to accept 2, so the valency is 2 in oxygen. So when I come to hydrogen, nitrogen, oxygen, carbon, nitrogen, sorry, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine is your 9th atomic number, 9. So write 2 and 7. Now write fluorine here. Now start filling the Lewis electrons. 1, 2, 3, 4, 5, 6, 7. Okay, right, 7 are done, fine. So I have 1 lone pair of electrons. So what is the valency now? Here 1 is the valency, because 8 minus 1 is 7, right? This is what. Let us write for neon, atomic number 10. So 2 and 8, 10. So it's stable configuration. So when you're writing neon, write capital N and small e. Now start filling electrons. This is stable. I have to write this. 1, 2, 3, 4, 5, 6, 7, 8. All are stable. What is the valency? This is stable. This is also stable. So the valency is 0. This is how we are going to write the Lewis dot structures. Careful, observe it, and please note it. Yes, students, so we have already drawn Lewis dot structures for atoms, that is a single elements. Now we'll be drawing Lewis dot structures for molecules. So let me pick up some certain examples. Let us go with the basic example, hydrogen. Let us write for oxygen. Let us write for a polyatomic atom, that is NF3. You can write for anything, NF3, NH3, okay, NH3 also. So let us read. Now for hydrogen, basically it is H and H, right? Now one electron is given by this and one more electron is shared by this. So this hydrogen gets a duplet here and this hydrogen also gets a duplet. So it has become stable. So how do you write this? H and H. This is how you will write Lewis dot. Now suppose this is for oxygen, right? Oxygen O and O. Always remember, okay, if I speak in terms of atomic number, oxygen atomic number is 8, it is 2 and 6, correct? So 6 is a valence electron. When I see always this particular 6 electrons when it is shared, for one it is 6, rather it is 6, so it's 12 electrons. The total number of electrons should be 12. But remember, just simple logic, oxygen, just register in your mind, oxygen will always form a double bond. With that I can fill the remaining electrons. If you remember this, wherever you find oxygen, double bond on one side, single bond on the other side, if it is 3 atoms. So remember, oxygen will always form a double bond. So with that criteria, this oxygen here, this also, I'm just giving you the clue. So 1, 2, 3, 4. Now fill the remaining till it becomes 8. 1, 2, 3, 4, 5, 6, 7, 8. Done. Now for this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Fill oxygen, because oxygen basically forms a double bond. So this looks like O double bond. Correct. Yes. Now when I speak about NF3, here compared to these two, you have to see the less electronegative atom in the center. So here less electronegative atom occupies is in the center. It should be in the center. So when I see compared to both, nitrogen is less electronegative compared to fluorine, because fluorine has an electronegativity of 4. So take this nitrogen right here, F3, F here, 2, 1 more and 1 more. Yes, now fill. Always fill first single electrons, right? This nitrogen and this one forms a single bond first. This nitrogen and this fluorine forms a single bond first. This nitrogen, this fluorine forms a single bond first. Once you are done with this, you can fill the remaining electrons. Let us see. 1, 2, 3, 4, 5, 6, 7, 8. Done. Now for this nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. It's done. Now for this nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Now let us see. This fluorine has octet. This fluorine has octet. This fluorine has octet. Now let us see for nitrogen. 1, 2, 3, 4, 5, 6. Yes, how many electrons are left out for attaining octet? 2 more electrons. So write those 2 more electrons. So how does this look now? N, single bond F, single bond F, single bond F. These are all single bonds, right? So single. This is the structure of NF3. If I write NH3, now in compared to both, which is less electronegative, hydrogen is less electronegative. But here when you are writing, you have 3 hydrogen atoms surrounding. So NH3, it is like this, basically your tetrahedral arrangement. So I have to show with Lewis dot structure. So show that Lewis dot structure. NH3 molecule, fill 1, 2 first. Fill. This hydrogen has got 2 octet, so duplet. This hydrogen has got duplet. This also has got duplet. How many are left out? 1, 2, 3, 4. So your lone pair is here. So it is NH3. If I write like this, just H3, this is your NH3 structure with the lone pair of electrons. This is how you're going to write Lewis dot for polyatomic. We'll meet again with some more examples. So let us see some more examples for molecules. So here, here you have carbonate. This is called carbonate ion, anion. This is called nitrite anion. This is in your ozone molecule, and this is called ammonium cation. Positive charge, so ammonium cation. So I have to write for all these. So carbonate, basically you have 1 carbon, 3 oxygen atoms. 1 carbon, yes, observe carefully, 1 oxygen atom, 1 more oxygen, 1 more oxygen. Yes, now I always said whenever there is a carbon atom, compulsory there is a double bond formation on one end. On any side there is a double bond formation. So here either you can pick up this or this. So I'm picking up this carbon, 1, 2, 3, 4. Done. So this carbon will share a bond with this oxygen. This carbon will share with this oxygen. Now let us fill the remaining electrons. For this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Done. For this carbon, this oxygen, so 1, 2, 3, 4, 5, 6, 7, 8. Done. Now for this one, 1, 2, 3, 4, 5, 6, 7, 8. Done. How is the structure looking now? It becomes C double bond O, because C double bond O, single bond O, single bond O, and you can fill the remaining, you can show the remaining electrons. 1, 2, there's already 1, 2, 3, 4, 5, 6, 7, 8. Here 1, 2, 3, 4, 5, 6, 7, 8. Here 1, 2, 4, 5, 6, 7, 8. This is your structure of carbonate ion. Let us write for nitrite ion. So when you are writing nitrite, careful, N, 2 oxygens, both the oxygens on both the sides. I already said oxygen will have a double bond character. Compulsory oxygen will have a double bond character. So fill the double bond either here or this side, not a problem. 1, 2, 3, 4, double bond. This nitrogen will form a bond with oxygen, 1 and 2. Now fill this, 1, 2, 3, 4, 5, 6, 7, 8. Now for this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. How is this looking now? Now I have to count for nitrogen also. So 1, 2, 3, 4, 5, 6. There are 2 more electrons, 7, 8. You have to write those also. So this looks in double bond O, single bond O, and you can fill and show the electrons. Yes, this is your oxygen with 2 lone pair of electrons. Let us write for ozone. Careful. Ozone molecule, the structure of ozone is this. Right. Now ozone molecule, as I said, oxygen will always have a double bond. You can put the double bond on this side and here and here, anywhere, but only one side. So try to put a double bond here. 1, 2, 3, 4. Done? Yes. Now this oxygen is bonded to this oxygen. See that. Now let us count, make the octet for this. 1, 2, 3, 4, 5, 6, 7, 8. Now let me see this oxygen now. Already 4 are on this side, 5 and 6, 7, 8. Let me count for this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Yes, fine. But remember one thing, oxygen having, because of this double bond character, there is always delocalization of electrons. That means there is shift of that pi bond. This is your sigma bond, this is your pi bond. This pi bond can always be shifted. Fine. So what do we do? When you're writing like this, right? If I write the structure, oxygen, double bond O, single bond O, right? This always is in resonance with, now this pi bond is shifted to this side, this becomes single, this becomes double bond. These are your resonating structures for oxygen. So now because of the resonating structures, sometimes this oxygen attains a partial positive charge and this becomes a negative charge, because you're shifting, right? When it loses this side, partial positive, and this is shifted to this side, this becomes negative charge. So you can write that molecule like that, positive and negative, only because of the shift of pi bonds or the pi electrons. So this is your structure of ozone. So when I come back to ammonium cation, so how many? Nitrogen in the center, hydrogen is, now I left something, I should write this minus also, right? Be very careful, write minus, remember that. Fine. So this ammonium cation, one hydrogen here, one more hydrogen here, one more hydrogen here, one more hydrogen, and there is a plus given. Right? So I have to show in terms of electrons, then I have to write the structure, right? 1 and 2. This hydrogen has got duplet, stable. 1 and 2. This hydrogen has got duplet, stable. This 1 and 2. This hydrogen has got duplet. This hydrogen has got a duplet. Let us see for nitrogen. 2, 4, 6, 8. This also has stable configuration. So how does this look? N, H, and H. And your plus is still there. Your molecule plus. That's what is ammonium molecule. So please note it carefully. Any doubts, please let me know in the comment section. Yes. So till now what did we do? We have learned Coussin-Lewis theory, and Coussin-Lewis, I already said, they're going to attain electron octet configuration by transfer sharing of electron. Then I gradually went drawing Lewis dot structures, where I have drawn Lewis dot structures for monoatomic, like simple elements like hydrogen, helium, lithium, beryllium, and then gradually I went into drawing Lewis dot structures for polyatomic atoms like ammonia, water molecules, carbonate, nitrite, ammonium cation, like that. Now let us see the exceptions or the anomalies or the limitations for octet rule. Basically we said octet means the particular element has to attain the duplet configuration or the octet to 8 electrons to become stable. But apart from that, there are 3 different groups or classes which don't obey octet rule. These are the limitations of octet. Let us see. So here you have electron deficient atoms, right? In electron deficient atoms, if I say, basically your group 1, group 2 and group 3 elements, and even group 13 elements, right? They form electron deficient atoms. For example, if I take group 1 elements, your alkali metals, group 2 alkaline earth metals. If I pick up the examples, yeah, like lithium chloride, lithium bromide, yeah, BeF2, right, BF3, all these are electron deficient atoms. Let me pick up one example and see. Suppose if I pick up lithium bromide, right, okay, lithium fluoride, let a smaller atomic number, let me take this, beryllium fluoride, right, beryllium is in the center, fluorine on either side, right. Beryllium atomic number, if I speak about beryllium atomic number, hydrogen, helium, lithium, beryllium 4 is atomic number, so 2 and 2, correct. So how many are there? 2 electrons, valence. So let us see, this beryllium will share a pair of electrons here. This also will share a pair of electrons here. So how many? 1, 2, 3, 4, 5, 6, 7, 8. Correct. Now for this fluorine, 1, 2, 3, 4, 5, 6, 7 and 8. Done. Now what happens here? Beryllium has 1, 2, 3, 4 only. Total number of electrons of 4. But here, is it getting satisfied? Is it satisfied with the octet configuration? No. What happened here? Only 4 electrons in beryllium. We are showing that 1, 2, 3, 4 electrons. I can't put 4, 5, 6, 7, 8. Why? Because beryllium doesn't have so many electrons. That is the reason it is called electron deficient atom. It is not forming. It is only electron deficient, and it forms BEF. BEF2. Just see, electron deficient. Let us see one more example. So I picked up group 1. This is also group 1 beryllium. Let us pick up BF3. So boron, 1 fluorine, 1 fluorine, 1 fluorine. This boron atomic number, if I speak boron atomic number is 5. So how many electrons? 2 and 3. So let us fill. This boron will give 1 electron to this, and this also will share 1 electron. This boron will give 1 electron. This fluorine will share 1 more. This boron will give this fluorine will share. Now let us write for fluorine. Boron 1, 2, 3, 4, 5, 6, 7, 8. Done. For this fluorine 1, 2, 3, 4, 5, 6, 7, 8. Done. For this fluorine 1, 2, 3, 4, 5, 6, 7, 8. Done. Yes. Now let us see for boron. Boron 1, 2, 3, 4, 5, 6 only. Yes. Now basically if I say boron trifluoride, it is only 5 electrons. Is it attaining extra? Does it have 8 octet configuration? Can I write 1, 2, 3, 4, 5, 6? 7, 8 can I write? I can't write. It's still having deficiency in electrons, electron deficient atom. That is why it is called electron deficient atom. So let us see excess electron then octet. There are some compounds called interhalogen compounds. Interhalogen compounds means intermixing of 2 halogens. For example, IF7. Just see, this is also a halogen, this is also a halogen. Both will intermix together and form interhalogen compounds. There are certain compounds called PCl5. Certain compounds like SF6, right? All these have excess electrons than the octet, right? They have more than 8 electrons. Let us see an example. Suppose if I speak about, basic example, PCl5. So 1 phosphorus here. 1, 2, 3, 4, 5. Cl, 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 Cl. If I write this in terms of Lewis dot, phosphorus 1, yeah. If I write this electron 1, 2, Cl, right? 1, 2, Cl, right? I'm writing this Cl. I'm writing this Cl. I'm writing this Cl. Right now observe carefully. Let us count. For phosphorus, how many electrons do we have? Basically, we need only 8 electrons. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has 10 electrons. Is it not excess compared to octet? That is why this category comes under excess than octet configuration. Please try for IF7 and SF6. It's the same. I'll write for SF6. Just see, I don't have place here. And I write. For SF6, if I write, I have to write S6 fluorines, right? 1, 2, 3, 4 finished. 1, 2, 3, 4, 5, 6 SFs. How many electrons now? 2, 4, 6, 8, 10, 12, 3, 14, right? The total electrons are, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, not 14, 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. I'm sorry, 12 electrons. Correct? So is it not excess than octet? So that is the reason that they come under the category excess octet rule. So let us come back to odd electron molecule. Basically, you have only 2 examples for odd electron. Let us write those 2 examples. One example is NO and another example is NO2. Right, this is nitric oxide, nitrogen dioxide. So let us write the structure. For NO, basically N double bond O. I said oxygen forms a double bond. So if I write in terms of Lewis dot, N 1, 2, 3, 4, 5. Correct? Now let us write the configuration for oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Now let us count for nitrogen. Basically atomic number of nitrogen is how much? 7. It is 2 and 5. Now total number of electrons is 7 only. How many? 1, 2, 3, 4, 5, 6 and 7. So look here, there is an odd electron on nitrogen. right? There's an odd electron. Instead of 8, it has an odd electron. This is called odd electron, single electron. So let us write for nitrogen dioxide now. So as I said, an oxygen will form a double bond character wherever it is. So oxygen on one side, single bond on the other side. How should I write and represent it? 1, 2, 3, 4, 5. So let us fill for oxygen now. 4 are over, 5, 6, 7, 8. Now this particular oxygen, 1, 2 here, 1, 2, 3, 4, 5, 6, 7, 8. Now let us count for nitrogen. 1, 2, 3, 4, 5 and 6. Yes, because the total 7 electrons, there is one odd electron lying in nitrogen. Yes, because of this, they come under the species odd electron molecules. So please note this carefully. Any doubt, please let us know. Yes, so students, we have taken one example for sp hybridization, that is BeF2. Now let us do one more example for sp hybridization, that is acetylene molecule. So acetylene formula CH triple bond CH. Okay, this is what I have to show with the hybridization, right? So when you are making acetylene, as I said, first step 1, try to make step 1. In step 1, you are going to write for carbon atom ground state. So carbon atomic number 6, electronic configuration 1s2, 2s2, 2p2. Correct? 2, 4, 6. Now this is table not required. So carbon in ground state. So 1s, so 2s I'll write. Right. In 2p I have half. Correct. Now this is px, this is py. Now carbon ground excited state, when I write, what should I do? One electron from here has to get excited to this because this is vacant enough. So 2s electron, half, 2s. From here, one electron will shift to this. So what do I get? I get this. This looks like this. Px, py, pz, half. Right? Now as I said, it is sp hybridization. Now observe carefully. 1s and 1p. 1s and 1p, this is your s and p, will combine and form sp hybridization. Observe, and these two will form this px, this is py, and pz will form pi bonds. This will form pi bonds. Remember that. Fine. So now I've got sp. How does this look now? This is your p and this is your s overlapped inside, like sp combined together. Now what should I do? I have to show all these in the form of hybrid orbitals. Let me make first. So I'm making for one carbon atom. For this I'm writing here. So first one I got s, the mixing this one. I still have py and pz orbitals. So this is your py orbital, this is your pz orbital. Correct? Yes, fine. So this is for one. I'm going to write. So let me make one line so that the diagram looks proper. Fine. This is for first carbon I made. Now I'm picking up second carbon. Now observe carefully. This is again the same thing, because for one carbon I got it like this. Now for the second carbon also I'm going to write like this. Yes, fine. So mix up that. Left over again, this carbon also will have py and pz. So make that py and make that pz orbitals. Now this forms one pi bond, this forms one pi bond. That is the reason how many? One sigma bond, one pi bond, one pi bond. So orbital, fine. This is one sigma, pi. This is how you're going to show. So what do we get? Done. Now hydrogen is still existing. This hydrogen has s orbital, so this will overlap and form hydrogen. Here this also will overlap and you will get this hydrogen. Yes, this is how we are going to draw structure for acetylene. So what do you find here? You have what type of hybridization is here? Sp and S. isn't it? Means the shape of hydrogen is spherical, so s orbital only 1s1, so sp s here. Now fine, so hope you've understood. I've written here I took carbon, I wrote the configuration, I wrote the ground state, I showed the excited state, then I pulled up 2 s and p. The remaining will form the pi bonds py and pz, py and pz. Then for this is for one carbon atom, for this I picked up one more, then I've joined both the carbon atoms and I've shown the pi bonds on both the sides. Yes, the leftover hydrogen atom is here and here. I'm still incomplete with the answer, so what else should I write? I have to write shape. Shape of the molecule is linear, correct? This is linear. Bond angle 180 degree, 180, right? S percentage character 50%. Look here, S is perfectly giving 50%. P character is again 50%. Type. What is a type? If I say, if I pick up carbon as 2, like A2, B2. If I make the monomer of that, it is AB, right? AB type to B2. Fine. So this is the thing. S character, linear structure, S character, P character, whole data is complete. This is how you are going to complete your answer, and at hybridization for your acetylene molecule. Please note it. Yes. So students, we've already done preparations of haloalkanes using alkenes, hydroboration, oxidation reactions. Then we have done from Grignard's reagent, from carbonyl compounds. So let me do the last preparation of alcohols from haloalkanes. Right. So preparation of alcohols from haloalkanes, right? Basically, there was a question asked from this. Let me write the question so that's easy for you to answer in the exam. Yeah. Why does aqueous KOH form alcohols when compared to alcoholic KOH, which forms alkenes, right? So just basic question, let us see. Whenever you see in the paper alcoholic KOH and aqueous KOH, only one thing should strike your mind, that is aqueous KOH will always give alcohols, alcoholic KOH we always give alkenes. Remember this, very important, alkenes. Let us see why. Now I'm going to explain this using an equation. Just see. Now I'm going to use, or I'm going to prepare alcohols from haloalkenes. That is, let me take C2H5Cl, right? Haloalkenes. I'm going to add KOH, that is aqueous. Fine. So immediately aqueous, as you see, you take out this KCl, add KCl, and the leftover is what? It is C2H5OH. Simple. Okay. Now let me write one more, C2H5I. I'm going to add aqueous AgOH. Okay, silver hydroxide. Then immediately your AgI comes out, and AgI comes out, and what do you get? C2H5OH. C2H5OH. Okay. Now question, I have to come back to the question. Just see, now I already converted haloalkanes to alcohols. Now aqueous KOH nature. What is aqueous KOH actually? Aqueous KOH is basically an alkaline substance, right? It is alkaline in nature. So it is alkaline in nature. When something is alkaline in nature, what happens? What does it release when it is dissolved in water? It's going to release OH minus ions. OH minus ions. So what are OH minus ions? OH minus is a strong nucleophile. It is a very strong nucleophile. So what happens whenever you have aqueous KOH in solution, because of the nature of OH minus, immediately this OH replaces this nucleophile which is weaker than that, and you get the required alcohol. So you will write aqueous KOH is a strong nucleophile and it is alkaline in nature, and it immediately replaces Cl minus, forming an alcohol. Now compared to aqueous KOH, I can pick up here your AgOH, aqueous AgOH will give you more yield. Why? It is mild in nature, right? It is mild, but compared to KOH it is mild, but the result on the products are good. Aqueous KOH yields are high. So this is how you're going to answer. Welcome back, students. So we've already started with the chemical bonding chapter, and all these days I've been doing theories. I first started with the theories or approaches towards chemical bonding. Now I'll be going into the topics, like topics basically means dipole moment, calculating formal charges, doing the hybridization concept, okay, properties of ionic compounds, properties of covalent compounds. So today the topic which I'm going to start is hybridization. Before I start with the topic, let me see what have I completed in this chapter. Yes, so I have completed VBT theory, I have done MOT theory, I have done Vesper theory. Yes, I've also done a concept called, or an approach called Kossel-Lewis approach. I have done all these. Please go through the videos and please send your suggestions and comments also. I've seen students not taking interest, because please remember, don't assume that grade 11 marks are not added to your board, so not a problem, we'll watch till the month of February. Please don't do that, because if you're aiming for your entrance exams, the basic first page or first word of your grade 11 till the last page of your grade 12, everything is important for your future. For you to be the future engineers or doctors, you have to study the basic of NCERT. So please go through the videos on regular basis and keep making or prepare your notes regularly. So let us come back to the topic hybridization now. So when I speak about hybridization, so in hybridization topic, basically if I define hybridization topic, how do I define? What have we studied? Basically in an atom we have an orbit and an orbital, right? What is an orbit? Orbit is basically a fixed path, as Bohr said, K shell, L shell, M shell and N shell, right? Those are fixed paths where you can find an electron moving. But when I come to orbital, orbitals are imaginary pathways, like imaginary, where the probability of finding an electron is maximum. Means you can find, but the probability of finding I can find this electron, but you can specifically mention or specifically fix the path of that electron. So orbital is an imaginary pathway and orbit as a fixed pathway. Now I'm speaking in terms of atomic orbitals. So atom, as I said just now, orbitals, what I just now explained. So now hybridization or hybridization process, mixing up of atomic orbitals. Mixing up of atomic orbitals. Which atomic orbitals? Of the same atom, like those particular atom of almost same energy, and the energy should be same. Intermixing of atomic orbitals of almost same energy to form hybrid orbitals. Hybrid means in the mixing of new orbitals. Rather, if I say in a normal language, it's called a formation of new orbitals. That is, so two atomic orbitals mix up to form a hybrid new orbital, which I'll be showing you. So note the definition for hybridization. Yes. Now let us see the types of hybridization. So two atomic orbitals are mixed up and you form a new hybrid orbital, which we are naming it as under giving them different names. So your hybridization basically are of many types. You will be studying in coordination compounds chapter in grade 12th also hybridization, but here in grade 11, if you understand the concept of hybridization, it is very easy for you to solve the chapter in coordination compounds in grade 12. Basically hybridization, if I speak types, you have three categories. Fine, let us see. Sp hybridization, Sp2 hybridization, Sp3 hybridization. Correct. Now these are all involving S and P orbitals. Now if I am involving D orbitals, you have hybridization like Sp3D. Right, I'm involving 1s, 3p and 1d orbital. Now further if I go sp3d2 more, further if I go sp3d3 hybridization. Now these are called outer orbital complexes. These are called outer orbital complexes. That means they are complexing, they're forming orbits to, they are mixing up, they're going towards outer side, S after P, then D. Now after this you have something called inner orbital complexes. Inner orbital complexes. In inner orbital complexes you have the combination. Now you have to start from inner side. Like now D comes in D sp3. This comes in D2 sp3. Okay, I'm just getting from inner side. Fine. Now we don't have D3 sp3, but as such you have one more combination D sp2. Fine, D sp2 is also there. Fine. So these are the different combinations of hybridization. I'll be showing examples for all, one after the other. I'll be showing how to calculate, how to write the percentage of S character, P character, what is a Bohr magneton, a magnetic moment. Please note carefully, and let us start with the first type of hybridization, Sp. Yes. Fine. So when I speak about Sp hybridization, yes, now let us write Sp hybridization. So suppose in the exam your ma'am or your teacher has given you an example stating like this. A particular molecule is given to you and they've asked you to write the hybridization, show the ground state, show the excited state, calculate the magnetic moment. How should you start? Suppose I have an example with me. Now for the Sp hybridization, for example, I'm going to pick up a basic example, BeF2, right? You can pick up a basic or an example of carbon dioxide. You can pick up an example of acetylene, right? All these have Sp hybridization, acetylene, Sp hybridization. Yes. So all these examples come under Sp hybridization. Fine. So now if I have to know like how will I know that it has Sp hybridization? I'll give you a small clue, see whether it works. Now for example, if I speak about carbon dioxide molecule. Now carbon dioxide structure, Lewis dot we have studied, C double bond O, C double bond O. This is carbon dioxide. Now observe, to know the hybridization, right? Simple thing. Sigma bond pairs plus lone pairs. I think this is the easiest way. Okay, sigma bond pairs per lone pairs gives a hybridization. Let me see whether this works. For this carbon, basically, if I speak about carbon, in carbon, how many sigma bonds does it have? How many sigma bonds? Now this is your sigma bond, this is your sigma bond, this is your pi bond, this is your pi bond, correct? So does it have lone pairs 1, 2, 3, 4, 5, 6, 7, 8? No, no lone pairs, right? So sigma bonds are, this is one sigma bond, this is one sigma bond. So how many bond pairs does it have? 2 bond pairs. How many lone pairs does it have? No lone pairs, 0. So 2 means 1s and 1p, Sp hybridization. For if I speak about oxygen, let us speak about oxygen now. In oxygen, how many does it have lone pair? Okay, let me write the lone pair. 1, 2, 3, 4, 5, 6, 7, 8. It has also lone pair. Now let me count. How many bond pairs does it have? Now this is sigma, right? Now this is sigma for this. Now for this particular thing, this is your this one bond, sigma bond, this particular bond. So this is one sigma bond, right? 1. Plus how many lone pairs does it have? 1, 2, 1. This is one set, this is one set, one pair, right? So 2. Total are 3. Total are 3 means 1s and 2p. Total are sp2. So this has sp hybridization, this has sp2 hybridization, this also has sp2 hybridization. That is how you're going to check the hybridization. So remember this, sigma plus lone pair is this. Count the sigma bonds, count the lone pairs and add them and see. So now let me write the example for the first example for BeF2. So when I pick up basic BeF2 molecule, your teacher has given you this BeF2. As soon as this is given to you, start your answer like this. First pick up beryllium, central atom. write the atomic number for beryllium. 4. Correct. Write the configuration 1s2, 2s2. Correct? Yes. Now, write the beryllium ground state. This is called ground state. Means it is not further excited. Write the beryllium ground state. So, 1s is stable, not required to write. So, write with 2s. So, 2s, how many are there? 1 electron, 1 electron. Fine. Now, this is your 2p orbital, p. Fine. Now, beryllium in the excited state. Now, beryllium has gone to the excited state. 1 electron from here will shift to this p orbital. So, what do we get? You have 2s half filled and you have your 2p half filled and all are empty. Now, this 1s and your 2p will hybridize together. I said atomic orbitals of the same atom will hybridize. So, this 1s and this 2p will hybridize together, forming, what do I get? I get 1s, 1p hybrid orbitals. So, sp. That is what we have written, sp hybridization. So now, how do these look? Now we said S is spherical in shape, P is dumbbell in shape. So S is spherical in, so your P is dumbbell and S will overlap. This is your sp hybridization for beryllium only. Now let us come back to fluorine. Now when I speak about fluorine, your atomic number of fluorine is 9. So write the configuration 1s2, 2s2, 2p, 6, 7, 8, 9, 10. So it should be 2p5, 5, 6, 7, 8, 9. Now 1s2 is stable, not required to write. Now I have to write fluorine ground state. So how is it looking? 2s2. Then you have 2p5, right? This is your thing. 1, 2, 3. This is over 4 and 5. This is ground state. Now observe carefully. This is stable. This is also filled. This is also filled. For how many? There is only one unpaired electron. This unpaired electron will go and hybridize or form a bond with this. This is which one? This is px. This is py. This is pz. So pz will overlap with the sp of beryllium. And how does it look? Structure of BeF2. So how many fluorines? 2 so far. So I'm going to write this here. So now let me make one line. Okay. Yes. Now center 1s, this p, and your this is of beryllium. Now pz of fluorine, as I said, p orbital is dumbbell shape. That p orbital will overlap with this. So this is your p orbital of fluorine pz. Now because I have one fluorine here, one beryllium here, I should also pick up one more fluorine with pz. This is pz. This is for fluorine. This is your hybridization structure. So how are you finding? It is linear, right? So when I pick up, it is like this, right? Be, F and F. The bond angle here is 180 degree. It is linear in shape. It is linear. So what are you going to conclude in the sp hybridization? You are going to write hybridization. I'll write a bit down. Hybridization is sp shape linear, right? Type AB2. We have studied in Vesper Theory AB2 type. Now percentage. S is, how much are you finding? Exactly 50%. S is 50% contributing. P also is contributing 50%. S is 50%. P is also 50%. Perfect. It is completely, your answer is completely done, right? So this is how you're going to write. So let us come back. Whenever an example is given to you, use that sigma bond pair plus lone pair, find the hybridization. After that, go with the central atom. Now this will be your step 1, this will be your step 2, right? Go with your central atom, write the configuration. After you write the configuration, write the ground state configuration for both, right? Once in the excited state, 1/2 electron will get excited to the 2p orbital. So now this S and this P will hybridize together. Now S, I very well know, is spherical in shape. P is dumbbell in shape. So combine both and you get an sp hybrid orbitals. Now let us come back to fluorine. Fluorine atomic number is 9. Write the configuration. Now keep filling electrons. 1s2 is here, okay, not required because already it is stable. So 2s2 I wrote, 2p5, 1, 2, 3, 4, 5 written. Now there is only one half filled electron that should get hybridized and form BeF2 molecule. So that half filled, that is pz orbital. Now I picked up this sp here, and this pz orbital dumbbell shape I made it to undergo hybrid intermixing of atomic orbitals. So the mixed up to get what is the type of hybridization here? We have sp this is sp2 hybridization. So this is sp, right? This is sp. So if I come here, it is sp p hybridization, means combining of s and p. Here also it's the same, sp and p hybridization. So finally come back and write type of hybridization is sp. Shape is linear and type is AB2. We have studied, right, in AB2, AB2L3 like that. AB2, S character exactly it is 50%, P character is 50%. That is how you are going to write for BF2. I'll meet again with acetylene molecule and carbon dioxide molecule. Yes, so students, we've already done the sp hybridization. So let us start with the second type of hybridization, that is sp2 hybridization. So let us write the heading sp2 hybridization. Yes. Basically, whenever we are studying sp or sp2 or sp3 or sp3d2 hybridization, we are more like we have to concentrate on the concept of how many s orbitals and how many p are intermixing together to form hybrid orbitals. That is most important. So as I said in my previous video, s percentage was so much, p percentage was so much, 1s and 1p in the same way. I'll also explain for this sp2 hybridization. Let us start with the class. So in sp2 hybridization, basically as the title suggests, you have one s orbital, yes, and you have 2p, right? Your px orbital and your py orbital intermixing together. So 1s and 2p. That's the reason we have called it as sp2 hybridization. So once I intermix or form a hybrid orbital, the shape of the hybrid orbital exactly looks like a triangle. It is just exactly like a triangle, right? How do the lobes arrange themselves? Put a dot in the center, one lobe above, one lobe here, and one lobe here, right? And intermixing of orbitals. How is the shape looking? Yes, it's looking just like a triangle, right? It is just triangle and it's in a single plane. That's the reason sp2 hybridization, we call it as the shape, call it as triangular planar structure. It is also called as triangular planar structure. So remember, 1s and 2p, they intermix together to form hybrid orbitals and finally attain a shape of a triangle, right? sp2, that means 1 plus 2, 3. So 3 lobes. Finally, they call it as triangular planar. So let us do this using an example. I'll take an example and let us draw the structures based on this. Fine. So whenever you're drawing sp2 hybridization, remember, careful, you have to go step by step. First, your teacher would giving you an example. You have to go to the ground state, excited state, the intermix with the orbitals, see how many are again forming pi bonds. Finally, I draw the orbital structure. Finally, write this character, p character, and write the shape of the molecule. So let us start. Let me pick up 2 examples for sp2. First basic example, BF3, and one more example is ethylene structure, CH2, double bond CH2. I'm going to pick up both the examples. Right, now this is boron trifluoride. So as soon as the molecule is given to you, so ma'am, how should I know whether it is sp2, sp or sp3? Yesterday I gave you a clue. Let us see that again. Whenever a molecule is given to you, write the structure. You have already studied the basic Lewis dot structure, isn't it? Yes. So if I draw the Lewis dot structure for this, how does this look? B, F, F and F, just join boron and this one 1 and 2, correct? Now 3 and 4, right? 5 and 6, done. Now fluorine, 1, 2, 3, 4, 5, 6, 7, 8. Lewis dot is complete. For this, 1, 2, 3, 4, 5, 6, 7, 8. This is also complete. For this, 1, 2, 3, 4, 5, 6, 7, 8. Fine. We very well know boron atomic number is only 5. So boron atomic number is 5. That means 2 and 3. Does it have any extra electron for boron to form? Not there. That is a reason boron is called as an electron deficient compound. Remember, I did in one of the video electron deficient compounds. So boron is an electron deficient compound. So what do I say? Now I have to calculate the hybridization for this. I told to calculate hybridization, just add sigma bond pairs plus lone pairs. That is what I told yesterday in the previous video. Sigma bond pairs plus lone pairs. So if I join this, if I come back to this, how many sigma bond pairs are there around boron? Now boron is a central atom. How many bond pairs do we have? 1, 2, 3. Correct, 3 bond pairs. Do we have any lone pairs? I said it is an odd electron compound. So odd electron, I'll write it here, odd electron. So do we have any lone pairs on this? We don't have any lone pairs. So lone pairs are 0. So 3 means, what do you say? 3 means Sp2, 2 plus 1, 3. That is how I said it is Sp2 hybridization. Remember that. Fine. So note this, and we'll start with the hybridization or intermixing of orbitals. Fine. So now what are we going to do? I'm going to take boron trifluoride. So BF3, our teacher has given us BF3. So I'll take, this is a central atom. This is your, to which it is going to intermix. So pick up the central atom. Write the atomic number 5. So it becomes 5 and 3. That means 1s2, 2s2, 2p. So 2 plus 1, 4. So boron ground state, if I write, it is 1s2 is already filled, stable. So pick up this 2s2, then 2p, write this 2p1. Fine. Now boron in the excited state. Now why should it go to the excited state? Because you should have 3 fluorines should intermix with them. That means you should have 3 vacant orbitals for fluorine to come and form a bond with boron. So this in the excited state, 1 electron from here will get excited to this. So you get half, then your 2p will be half and half. This is 2s and this is 2p. So now what happened? How many orbitals do we have? S and P2, right? Now 3 fluorines are there, 1 here, and 1 here, isn't it? So all the 3 fluorines will intermix up. Fine. So now this is done. So now S and P, Sp2 has to intermix. So how do they look like? Now if I take, now this is your P orbital and your S orbital, correct? Yes. Now this is intermixing, but still I am not done. But now what should I do? I have to pick up the F orbital and I have to intermix with this, correct? Yes. Now let me write the state for fluorine and see what's going to happen. Yes. Now when I pick up for fluorine, so let me write this later. And I'll use the board. So fluorine atomic number is 9, 1s2, 2s2, 2p, if I write 6, 7, 8, 9, 10. So this is 2p5. So let's fill the ground state 2 and your 5, correct? 1, 2, 3, 4 and 5. Now for one fluorine you have 1 vacant orbital. If I take this as 2s, if I take it as 2p, px, py and pz, for one fluorine you have 1 half filled, right? For 3 fluorines you have 3, right? So these 3 will come and join here. Right, 1 fluorine is 1, so 3 fluorines you have 1 vacant space here, 1 vacant space, 1 vacant space. So you want to draw those vacant spaces and you want to show the structure. As I said, what did I say? It is BF3. How is the structure? I said it is in one plane. 1s and 2p will mingle in one plane, isn't it? So how do the structure look when they intermingle? This is 1, this is your this orbital, this is your, right? Now your lobes intermixing exactly. Now if I draw, this is a triangle, right? Exactly, if I draw a triangle. Now still I'm not done. Yes. So now what happened? Now these S orbital and P2 orbital have intermixed and formed triangular structure. So let me be clear without a mistake. So 1, correct? 2 and 3 lobes. Yes, this intermixing. Fine. Now I have F, right? This and this is mixed up and form a triangular planar structure. Now this F, how many F's we have? 3. Which orbital of F is there? PZ. So take the PZ orbital, intermix with this PZ here. You have PZ here and you have PZ orbital here, right? So now here what is the bond? Here this is Sp2 hybridized bond, correct? Now here what is the bond? This is Sp2p. Yeah, here also what is Sp2p? Sigma bond, correct? Yes, Sp2p sigma bond. Here what is the bond? It is Sp2s sigma bond. Here what is the bond? Here also it is the same, Sp2p, no? Not S, it is Sp2p. How? Sp2 of these two, P of this, Sp2p sigma bond. So these are the bond. This is how you're going to draw structure for BF3. If I basically see, isn't it looking like a triangle? So that's the reason we call it as triangular planar. So once again, so first as soon as the element is given to you, write the ground state. Right, first write the configuration, then go to the ground state, then go to the excited state. Now one electron got excited, so Sp2 hybridization. So they intermix together. So once they intermix, I very well know Sp2 hybridization, they are going to intermix and form triangular planar structures. So triangular planar structure. Now write the fluorine atom. How many fluorines we have? 3 fluorines. Write the ground state configuration of fluorine. When I say there is only one unpaired electron, correct, which is in p orbital. So how many fluorines do we have? 3. So intermix that fluorine, 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 and finally show the triangular planar structure. Is my answer complete? Not complete. I still have to give the data. Shape of the molecule is triangular planar structure, correct? Yes. What is a bond angle? Here if I take the bond angle is 120 degrees. So bond angle is 120 degree, correct? What is the S correct S percentage? It is, how much are you saying? It is 1:2, right? So 33% of S character and P percentage is 67% of P. Together makes it 100%. So your basic data, this should be complete with your answer. So go through the whole thing. Please note it carefully. This is important. This is important. This also is important. This is also very important when BF3 structure is given to you. Yes, so let us start with the third type of hybridization, that is Sp3 hybridization. Yes. So as the name suggests, Sp3 hybridization, basically we have 1s plus Px Py and Pz orbitals intermixing. So intermixing of 1s and 3p orbitals is called your Sp3 hybridization. So I made the structure. Let me make this properly. Yes. Yes. So the intermixing of 1s, Px, Py and Pz is called Sp3 hybridization. When these intermix together, the structure which, or after intermixing, after forming the hybrid orbitals, the structure looks like a tetrahedral structure. So remember, Sp3 means tetrahedral, Sp means linear, Sp2 means trigonal planar, right? For tetrahedral structure, how do you get a central atom in the center? There is one angle here, one sigma bond and one more, and these are shorter because they are going to rarer end, and this is like this. So the tetrahedral structure resembles this exactly. You'll be getting it like this. So if I join this tetrahedral, the longer bond, but you have to join these also and form a bond directly. So let me draw the tetrahedral structure and show it to you. So let us start. First, let me pick up. So as I said, 1s, px, py and pz. So let me take an example for tetrahedral structure and show you. Basic example and the most famous example is methane molecule. So methane is an example for tetrahedral structure. So methane CH4, correct? Yes. Now write the structure. 1 hydrogen, hydrogen, here one more hydrogen, here one more hydrogen. Now again I'll use that formula to find hybridization. As I said, to find hybridization, I have to use the formula sigma bond pairs plus lone pairs. This is what I have to use to know whether it is correct or not. Sigma bond pairs, how many sigma bond pairs do we have? 1, 2, 3, 4. 4 sigma bond pairs. Do we have lone pairs? Let me count. 1, 2, 3, 4, 5, 6, 7, 8. No lone pairs, 0. So what is the type of hybridization? Sp3 hybridization. This is how we are going to do Sp3 hybridization. So let us start with the structure. So as soon as I have to draw step 1. What is step 1? I have to write the atomic number for carbon first. 6. Right? 1s2, 2s2, 2p2. So you're going to write electronic configuration carbon ground state. How does this look? This is 2s2. This is 2p, half and half. Correct? Now carbon excited state. One electron from here will get excited to 2p. How does this look now? This is your 2s and you have 3p half filled p orbitals. This is s, 2s, this is px, this is py, this is pz. Now during hybridization, 1s and 3p will combine together and forms sp3 hybridization. That is why we call sp3 hybridization. Now these particular, now when I'm trying to draw, now I've got a conclusion, I've come to a conclusion. Now ma'am, why have 4 we have 4 hydrogens, so we need one vacant space here, here, here to intermix or for the hydrogen atom to come and form the sigma bonds. So let us draw the diagram. How to draw the diagram? Yes, for methane molecule, I said what is the structure they show? It should be exactly a 1 bond here, 1, 1 and 1. I want to use the same structure and draw the CH4 molecule. Now in the A position, this is your central atom, carbon. Okay, yes. Now your first, these will intermix. I said it looks like one lobe here. Yes. Now you have 3. This is here, shorter. This is towards you, and this is your bond. Okay, now you have intermixing of orbitals. I made a bit this one, intermixing of orbitals. Yes, not still not complete. These are all sp3 hybridized orbitals, right? Now you have 4 hydrogens, 1 hydrogen here, 1 more hydrogen here, 1 more hydrogen here, 1 more hydrogen here. So this is your hydrogen atom, this is your hydrogen, this is your hydrogen, this is your hydrogen. So what is the type of hybridization here? This is sp3s hybridization. Here also sp3s hybridization, sp3s hybridization, and here also sp3s hybridization. Yes. Now what is the bond angle? Bond angle is 109 degrees 28 minutes. For tetrahedral, the bond angle is 109 degrees. But if there are certain lone pairs, there are certain variations in water molecule where it will go down to 104. That also I'll explain. So am I complete with the answer? I'm not complete. I still have to write the basic data. So what is the basic or the important data? What data should I write? Here, shape of the molecule. Shape is tetrahedral. Then what is the bond angle which I wrote just now? Bond angle is 109.28. Yes. Next, S percentage. S is 25% and P character is 75%. This is your answer. Once again, as soon as your molecule is given to you, first do step 1. As soon as this is given to you, first write the structure. Once you write the structure, please find out which type of hybridization is this. Once you find the type of hybridization, come back and write the electronic configuration. After writing the configuration, write the ground state. After ground state, you are going to write the excited state and show how many are intermixing. Now we very well know sp3 hybridization means the shape of the molecule is tetrahedral. So draw the lobes in that direction. Once you are done with that, now you have hydrogens, 4 hydrogens. As we very well know, hydrogen forms sigma bonds, right? Hydrogen is 1s1, so bonds. Right, one hydrogen. So 4 hydrogens on all the sides. Then write the bond angle, then show the shape, bond angles as percentage P, and your answer is complete. Please note it. So let us do one more example for sp3 hybridization. So the example which I'm going to pick up is ethane. For sp3 hybridization, so I'm going to pick up ethane. What is ethane formula? Eth means 2 carbons, right? So C single bond C. So around carbon 4 valency 1 and 3. So let me write hydrogen as 1, 2, 3. This is easy for me. 3 hydrogen, hydrogen and hydrogen. As soon as this molecule is given to me, I have to check whether the hybridization is sp2, sp or sp3. So what did I say? Calculate the formula sigma bond pairs plus lone pairs. Right now sigma bond pairs, this is sigma, this is sigma, sigma. So 1, 2, 3, 4. For this carbon it is 4. Fine. So how many lone pairs? Does carbon have lone pairs? How should I calculate lone pairs? Just count 1, 2, 3, 4, 5, 6, 7, 8. So lone pairs are 0. Yes. So if it is 4, it means it is sp3 hybridization, because 3 plus 1, 4. Yes, now done. Come back. Now I have to write carbon atomic number 6. So write the configuration 1s2, 2s2, 2p2. Now write the carbon ground state. Carbon ground state, what do you get? So 2s2 is filled, 2p2 is half filled, 1 and 2. Yes. Now carbon excited state, 1 electron from here excites to this part. So what do you get? 1s. So this is 2s half filled. Yeah. And your P3 are 1, 2, 3. Px, Py and Pz. All the 3 are going to get, or they're going to form hybrid orbitals and forming sp3 hybridization. Yes, fine. So this is your thing. Now I have got the basic data. They are going to intermix together to form sp3 hybridization. Now I have to draw the shape of the molecule. Now I already said for sp3 hybridization, how should the shape be? The structure looks exactly like this. You know, this is A. This is one low. This is a shorter. This is a bit long towards you, and this is your this. Yeah, it looks like this tetrahedral. So draw the structure like this. But here we have 2 carbon atoms, isn't it? Correct? Yes. So what am I going to do? I'm going to hold this A and just shift. Like, no, it's exactly like this. I'm just going to rotate. So what do I get? Put 1 dot here for this carbon. Put 1 dot here for this carbon. One has to form a sigma bond with this sigma bond. Intermix. This is going to form a sigma bond intermix. Done. Now this is your carbon atom, this is your carbon atom. Done. Now how many do we have? 3 hydrogens, right? So 1 is towards this, 1 is towards this, and 1 is towards this. Yes, the same the other side. Towards this, yeah, 1 orbital here and 1 more is correct. Done. Now what happened? We have three hydrogens on this side, 3 hydrogens. S orbital of hydrogen, S orbital of hydrogen, S orbital of hydrogen. You're going to intermix, or they're going to form beta orbitals. So what is this slope? From where did we get this? By intermixing of S and 3 p's, right? So this is sp3 S orbital sigma bond. Sigma bond. Now what is this one? sp3 hybrid orbitals, because they have intermixed, right? 1s and 3p. Yes, sp3 intermix. So this is again sp3 s orbital. This is hydrogen, 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 hydrogen. All these are sp3 sigma hybrid orbitals. As hydrogen always forms sigma bond, so sp3s, 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 sp3s hybrid orbitals. So this is your shape of ethane molecule showing tetrahedral arrangement. This is your arrangement. Now once I have to complete the answer, as I said, you have to write shape of the molecule is tetrahedral. Yes. What is the bond angle of the molecule? As I said, bond angle is for tetrahedral 109 degrees 28 minutes. Correct? Yes. What is the S percentage character here? Earlier I said 25% of S character, and P character is 75%. Yes. So is the answer complete? Shape is done. Hybridization. So as I said, okay, hybridization is sp3. 1s and 3p. 1s and 3p. So this is your answer. This is how you're going to write. As soon as a molecule is given to you, write this first. Then go to this step. Second step. This is the first step. Second. Then write this as third step. Then this is your fourth step, this is your fifth step. That means you should write 5 steps for any hybridization molecule given to you. Then your answer is complete and you'll be getting 3 marks for this answer. Yes, so students, let us do 2 more examples for your sp3 hybridization, that is ammonia and water molecule. So when I am giving this molecule ammonia and when I am giving this molecule water, yes, let's see. Basically, these also show sp3 hybridization, but they belong to a category called, now ammonia belongs to a category called B3L. That is, there is one lone pair of electrons, right? Now water belongs to a category called A. This is your A, B2 and L2. There are 2 lone pairs of electrons. So let us see how are we going to draw the structure for hybridization if this question is given to us. So for ammonia, when it is given, let us write the central atom nitrogen. Atomic number 7. 1s2, 2s2, 2p, 3. 3, 4, 5, 6, 7. So now start. Ammonia, nitrogen ground state, you're going to take, draw the configuration 2. Correct. Now p orbitals are 3 half filled, 1 2 3. Because it is showing sp3 hybridization, yes, this s and these 3 p3s are going to combine and hybridize. This is px, this is py, and this is pz. Yes. Now how are they going to hybridize? Fine. Now what do we have? We have an extra lone pair in nitrogen. Let us show that. Ammonia is basically, or as we said, as it's going to show sp3, the structure would be sp3 but a slight variation in the bond angle. How? For sp3, how did we draw? We took this A, we have drawn this, and we have made the structures like this, isn't it? This is what we have made for sp3. But here, let us observe for nitrogen ammonia. Put nitrogen in the center. Yeah, you have your one lobe, this one. You have 3p where your hydrogen is going to go and just join. Just see. This is your hydrogen. This is your px orbital. This is one more orbital and this is your third orbital. Now we have 3 hydrogens, isn't it? One forms one hydrogen bond, one more hydrogen bond and one more hydrogen bond. This is your hydrogen atom, hydrogen atom, hydrogen atom, and what is this hybridization? These 3 have formed due to sp3 hybridization. So sigma sp3s. This is also sigma sp3s. This is also sigma sp3s. Now here this particular thing has a lone pair of electron. Yes, because of this lone pair. Now this is called L dot P, lone pair. This is called bond pair. Now what happens? Because of the lone pair bond pair repulsions. So I'm writing a new word called LPBP repulsions. Just see, lone pair bond pair repulsions. Yes, what do they do? What are repulsions? They're going to repel each other. Yes, opposite poles attract, and similar, both are electrons, right? This is also an electron, this is also an electron. So like poles and like poles, right? Like poles, they're going to repel each other. Fine. So because of this repulsion, lone pair bond pair, the bond angle basically for sp3 it was 109 degree 28 minutes. Now here the bond angle has decreased to 107 degree. Here for nitrogen the bond angle has become 107 degree. Why? Because of lone pair repulsions. You should always remember LP repulsions are greater than LP bond pair repulsions are greater than BP repulsions. You have to remember this. Because of this, the bond angle has come down. So let us write now. S character is how much? 25%. What is P character? 75%. What is the bond angle? 107 degree. What is the shape of the molecule? Yes, because of this lone pair bond pair, from tetrahedral it has become pyramidal. The shape of the molecule is pyramidal. Remember that. Now let us write for water molecule. Here this is forming this is an s orbital, so we're going to pick up oxygen here. Oxygen, atomic number 8. So 1s2, 2s2, 2p, 4, right? 4, 5, 6, 7, 8. So oxygen ground state, just fill it. So 2s orbital, so 2 electrons. So p orbital has 1, 2, 3 and 4. Yes, so this is your px, this is your py, this is your pz. Now your s orbital and p orbital are overlap, but only difference between here also s orbital and p orbital, but here you have one lone pair, here you have two lone pairs of electrons. Remember that carefully. So these form sp3 hybridization. How do they look? The structure is similar, but the bond angle is different. So here you're going to draw one. This is your oxygen atom in the center. Yes, now this 1, 2, 3. Yeah, this is like this, the first one, and you have the second one, and this is the third one. Yes, so what happened? Now observe carefully. How many hydrogens do we have? You have one hydrogen here, you have one more hydrogen here. So this is your lone pair, one pair. This is one more lone pair, lone pair. Now what are you observing? Here you have lone pair, lone pair. Here you have lone pair, bond pair. So let me write. Here you have lone pair, lone pair, this is your bond pair. Now what happens is, as I said, this is what I said, lone pair repulsions are stronger, then comes lone pair repulsions, then bond pair. Now what happens? Because of this and this repulsions, this is having an impact on the bond pair. Yes, observe, this and this will repel, and this will have an impact on bond pair. So now what happens? The bond angle from 107, it has become 104 degrees now. 104 degrees, 0.5 minutes. It has become from 107, it has become 104 degrees. Why? Because of your LP-LP repulsions and LP-BP repulsions. Because of this, the bond angle, this is going to push this bond here, this is going to push this bond pair together, and finally the bond angle reduced to 104 degree. So what is the shape of the molecule? Now you have to write same. S character 25%, P character 75%, bond angle is 104 degree. Why? Because of lone pair repulsion as well as lone pair bond pair repulsion, and the shape of the molecule will be bent. It will be a bent structure because it is completely bent, a V-shaped, bent V-shape, inverted V. Exactly. So all these, if you join, it's like this, this is joined like this, this is joined like this, and this is joined like this, this is also joined like this, a bent structure. So this is also the same story. Join here, join here, join and join structure. So ammonia molecule, write the configuration for nitrogen, write the configuration for oxygen. Ground state only you will get sp3 hybridization, ground state only you will get sp3 hybridization. After that you are going to draw the structure. We very well know in nitrogen there is one lone pair, and here 3 hydrogens are going to fix. 1, 2, 3 hydrogens, and the fourth one is lone pair. Now lone pair bond pair repulsions are more, right? Because of this, from 109 degree it has come down to 107 degree. And finally you will overlap with hydrogen atoms. Here what type of hybridization it is? sp3s, sigma. Okay, sigma sp3s. Then you are going to write S character, P character, bond angle and shape. Same here with water molecule. Oxygen, will pick up the atomic number, write the configuration, fill the electrons, and show that lone pair repulsions and lone pair bond pair repulsions have reduced the bond angle from 109 to 107, 107 to 104 degree, 5 minutes, and finally write the bent structure of water molecule. Please note it. Yes, so students, we've already done sp hybridization, sp2 hybridization, sp3 hybridization, and also completed sp3d hybridization. So let's come back to the last type of hybridization, that is your sp3d2 and sp3d3. Right. When I speak about sp3d2 hybridization, sp3, let us see what are the orbitals which are intermixing. Here you have one s orbital, right? You have px, py and pz orbitals in the mixing. Along with that, in d orbital, what did I say in sp3d? We have, I said dz square is in the mixing along with p. Here you have a combination. We need how many? 3, 4, 5, 6, right? 1, 2, 3, 4 are done. I need 2 more. So dz square and dx square y square also is going to mix up. They mix up together to form sp3d2 hybridization. Now when I come to sp3d3, it's a similar thing but extra d orbital. One is px, py and pz. Along with that you have dxy orbital mixing up, dx square y square also mixing up, and dz square. So total how many? 1, 2, 3, 4, 5, 6, 7. 3 plus 3, 6, 7. Yes, done. So these are the orbitals which are intermixing together and finally giving us sp3d3 and sp3d2. So let us see the example for SF6. So as soon as this element is given to us, what should I do? I have to take the central atom and write the configuration. Sulfur is 16, 1s2, 2s2, 2p6, 3s2, 3p. So if I write 4, 4, 5, 6, correct? Now right. Now sulfur ground state. In sulfur ground state, what happened? This is all stable neon configuration. I have to write only these two. This is your 3s, right? And you have 3p, 1, 2, 3 and 4. Your 3p is done. Now what happened in the excited state? Yes, sulfur in the excited state, 1 electron. Yeah, so what should we do now? We need sp3d2, right? Yeah, observe, 1 electron from here and 1 electron from here. 2 will jump to the d orbital because I need d2, right? So what should I do? I'll just take this a bit here. Yeah, sulfur excited state, 1 in the excited state, 1 3s. Next, in the 3p you have half filled, and now next will be your 3d, right? 1, 2, 3, 4, 5. So 1 electron from here will get excited here, 1 electron from here will get excited. So what did I say? 3z square as well as 3x square y square. Correct? So all will mix up together and form sp3d2. So let us do for iodine. Iodine we very well know. The outer configuration of iodine is 5s2, 5p3. 5p5, right? So it is 7, 5p5. So 5 plus 2, 7. So let me write the ground state of iodine. Yes. So we have 5s2 and you have 5p5. 1, 2, 3, 4, 5. Correct? So this is your 5s and this is your 5p. Now observe iodine in excited state. Yes. Now we have what? We need 3d3. So 5s half filled, 5p half. Now how many electrons? This electron gets excited, this electron, this electron. All the 3 will get excited in d orbital. So 1, 2, 3, 4, 5. So what did I say? What will participate? dxy, dx square y square and dz square. So 1 electron from here will get excited to this place, 1 from here and 1 from here. So what do we get now? We get sp3 D3 hybridization. So this is what is a hybridization. Now let us draw the structure. So when I speak about the structure, your SF6, simple. How many are there? 3, 4, 5, 6, right? 6 means octa. Yeah, in chemistry we call it as octa. So octahedral structure. So SF6 has octahedral structure. Observe carefully. Draw sulfur at the center. Yeah. Now you have axial bonds, correct? I told you earlier, axial bonds. Yes. So done. 2 are done. How many are still existing? We have 4 more. Yeah. 1, 2, 3, 4. F, and F. Equatorial bonds. Yes, this is your octahedral structure of SF6. Suppose if I speak now here, when I see the bond angle, if I just draw the line, the bond angle here perpendicular to this, if I draw, it is almost 90 degrees. If I take this also, if I draw this line, it is 90 degrees. Now if I draw IF7, so here how many are there? Total 3 plus 3, 6, 7, right? 7. So then it is called as pentagonal bipyramidal. Remember, how does this look like? For iodine, draw iodine in the center. Okay. First put axial bonds here. F and F. Important. Now we are left with 5 more. Now try to make a pentagon. So a pentagon looks like this. If I draw, okay, a pentagon. Just see how many? 1, 2, 3, 4, 5 pentagon. So what you do? You try to join these. This is fluorine. This is fluorine. So how many row? 1, 2, 3, 3, 1, 2, 3, 4 row. Now I have to join. This is 5, right? This is 6. This is 7. Okay, right. So how does this look now? This looks, if I take out this pentagon and join, and if I only see fluorine atoms, how does this look? For you to understand the pentagon, I've drawn it. So you can also leave it in the exam like that, but you can also just erase it also, not a problem. Finally you get a pentagon. So let us see whether all 7 are there. 1, 2, 3 on this side, 3 on this side, and here F is this. So your pentagon structure, all the 5, 7. If you're because these are towards yourself and this goes into the board, so I have 7 structure. The name of the structure, now the bond angle is almost 72 degrees, and the shape is pentagonal because pentagonal, this is your pentagon, bipyramidal structure. Yes, so this is your structure basically for sp3 and sp3d2 and sp3d3. So let us see once again. Once the structure is given to you, just see what are intermixing both the sides. After that, pick up the example which is given to you. Done. After that, write the ground state configuration for both. I didn't with the atomic number, large atomic number, so try to remember that. It is 5s2, 5p5. So I'm going to write first the ground state. Here also I've written ground state. Then I went to the excited state because I need D2. I have excited 1 electron from here and 1 electron from here because I need 2 D orbitals. Here what did I do? I've excited I need how many? D3. So 1 from s orbital, 1 from P, and 1 more from P. So D3 I got. Then I've drawn the structure. Octahedral. How did I know it is octahedral? Because it is SF6. 6 ligands are participating. Here there are 7. Fine. 7 means apart from this pentagon structure, you have 2 more on the axis, axial bonds. 2 more. So I've drawn the bond angle on both. I've drawn the structure octahedral and pentagonal bipyramidal. This is how you're going to draw for sp3d2 and sp3d3. Please note it. So they've given me this question, and let us see, they've asked us based on the dipole moment. Let us see the question. Why does BF3 possess 0 dipole moment compared to NH3? So now, this is your BF3 structure, this is your ammonia structure, correct? Yes. So BF3 structure, if I speak in terms of the electronegativity, here fluorine, the electronegativity is 4, correct? Now here hydrogen, the electronegativity is 2.2. Nitrogen electronegativity is almost 3. Okay. Yes. Now boron electronegativity is, it is around 2. I'm just not specifically saying 2.3 or something. Now though there is lot of, now look here the electronegativity difference is very less, but then too it has dipole. Here the electronegativity difference is more, but then too it has 0 dipole. That is what they're trying to ask you. Let us start. Now here what happened when we see the structure of the molecule or geometry of the molecule, yeah, this is dragged by this fluorine, This is dragged by this fluorine, this is dragged by this fluorine, isn't it? Now observe. According to parallelogram law of forces, yeah, what happened? The resultant of these two is equal and opposite to the third one. That is what is your parallelogram law. Yes. Now the resultant, what is it? Because of this, what is the resultant? This is the resultant of any two is equal and opposite to the third one. So these two gets cancelled with this. Yes. Am I getting? So according to parallelogram law of forces, what should you write? Resultant of any two is equal and opposite to the third one. So these two opposite to the third one, so this gets cancelled and finally mu becomes 0. Yes, but in this case what's happening? Yeah, this is dragging, so these electrons are dragged towards the electronegative nitrogen atom. This is also dragged, this is also dragged, so the whole, again you have a lone pair of electron, the whole electron density is dragged towards nitrogen, and hence it poses 1.49, almost 1.49 d by value, d by Huckel, no, d by value of dipole moment with that. So here there is the geometry of basically the geometry of the shape is deciding the dipole moment. That is what I said in applications, geometry decides the dipole moment. Here it is in this geometry, dipole moment has become 0, but here it is in this geometry. Here also we have three atoms, here also we have 3 atoms, but because of the shape of the molecule, the dipole has completely changed, giving this a structure of the bond angle. What is the bond angle here? Almost 107 degrees. It's giving a particular bond angle, it's giving a particular geometry to that. So this is how you're going to explain the structure and finally finish off the answer. So because of the parallelogram law of forces, this has attained this law, and here nothing, difference in electronegativity, though it is more because of the geometry, so we will write though electronegativity difference is less because of geometry, ammonia possesses, or it has mu is equal to 1.49 d. This is how you're going to answer. So students, we've already done the theories, then I've completed the hybridization concept. Now we'll go to the next concept, that is dipole moment. Right. So when I speak about dipole moment, I know most of the students get confused with this. It's very easy actually. So dipole moment is basically separation of charges. Just remember one word. Suppose if you're not able to remember the whole concept, remember it is separation of charges. Suppose if I have one cation here, I have one anion here, there are two, and you're linked or they're connected from the nucleus, that is your bond length, right? The distance between this, or the product of the distance and the charges of them, is dipole. Okay, what am I trying to say? Dipole moment is basically, suppose you have an atom A and you have an atom B. Okay, fine, right? Otherwise, if I take for ionic compounds, 2 ions. This particular thing has a partial positive charge and you have a partial negative charge. These two are connected from the center of the nucleus by a distance r or d, and the charge of this, now positive charge q1, negative charge q2. Now what is dipole? Dipole moment is represented by mu. Mu is equal to the product of the charge. So instead of the charge, I'm picking up as a single entity E. E is charge into the distance d. So E stands for charge and D stands for the distance or the bond length. Correct? Yes, distance between the two atoms. Now this particular U or mu is measured in terms of, or by a chemist, dBi. So they measured, we take mu as dBi. So dBi. So dBi stands for capital D. Okay. 1 dBi is equal to 10 raised power of minus 10 ESU dot send it. What is this? What is ESU? ESU means electrostatic unit charge. So I'm writing that also here. ESU stands for electrostatic unit charge. Yeah, and the distance. Okay, and the distance between them. This also is equal to 10 raised power of minus 18 stat coulomb dot. What is stat coulomb? Basically, stat coulomb is something which we consider for smaller charges, like very minute, like electropositive dipole moments. Like smaller charges, I consider stat coulomb. So stat coulomb is for smaller charges. Otherwise, you consider coulomb, isn't it, for calculating the charge? Fine. Now, means a basic electrostatic force of attraction created among two smaller atoms. This also is equal to 3.33 into 10 raised power of minus 30 coulomb meter. This is also one of the unit for your dipole moment. Fine. I've learned the basic thing. I've learned the units, right? Now, I have to know on what conditions is the dipole created. When is the dipole created in the molecule? That is important for us. So apart from this, once we are done with this, so let us write the conditions for the dipole momentum. So let us erase all this and write conditions for dipole moment to occur. Yes. Right. Now, for a dipole moment to exist or a dipole to exist in the molecule, first most important thing is the molecule should be polar in nature, right? It should be polar, or it should have polarity, polar in nature, polar. Okay, it should be polar. What does this mean? Polar nature. I'll explain why. So, when do I get polarity, or when do I get difference in charges? When there is an electronegativity difference, isn't it? We have already studied what is electronegativity. The ability to drag the shade pair of electrons. They're going to drag the electrons. All the non-metals like fluorine, chlorine, bromine, iodine are electronegative in nature. So, they should find, you should say, there should be electronegativity difference should be high, should be more or high. For example, suppose if I speak about some, let me take this order. So electronegativity difference should be high means, suppose if I take hydrogen, fluorine. I just now told you fluorine, chlorine, bromine, iodine are highly electronegative in nature. So HF, HCl, HBr, okay, HI. When I speak about hydrogen, the electronegativity is 2.2. Mu is 2.2. Fluorine electronegativity is 4. Okay. Yes. Here it is 2.2 and 3. For hydrogen it is 2.2 and it is almost 2.8. Now, remember. Apart from this, for calculating mu, I also require the distance, bond length also, isn't it? Yes. So, when they have calculated the bond length, the multiplied bond length and charges together, they have got almost a value of mu equal to 1.98 for HF. And for HBr, they've got a value of 0.98. So, almost 98 or 99. What are you finding? What difference are you finding? Larger the electronegativity or higher the electronegativity, more is the dipole. Remember the first point. So what should you conclude from this? Now see, the electronegativity is more, so the dipole is more. The electronegativity is less, so less the dipole. So what should you write? Remember, why? Because it is highly electronegative, it is trying to drag the electron pair towards it. When it is dragging the electron pair automatically, now suppose this is your fluorine here, this is your hydrogen. When this is trying to drag the electron, this will get negative charge and this will get positive charge, correct? So, higher the electronegativity, higher is the dipole, higher is mu. Remember this. When your teacher asks you if why is this, what is the reason, you can write if the electronegativity is more, the pull of the particular electron is more. If the pull of electron is more, automatically they get dipoles, two charges on both of them. So this is your mu, higher the dipole. Now next important thing, whenever you are expecting a molecule to have dipole, the geometry should be particularly very important. The geometry, what am I trying to say? Geometry means shape of the molecule. Geometry or shape of the molecule should be correct. Means it should be shape of the molecule should support, actually, or shape of the molecule should support. What am I trying to explain by this? Let me take an example. Observe carefully. Suppose I have an example CH4, methane. Okay, I have an example like CCl4. Okay, I have an example like water. Okay, I have 3 examples. Correct. Now observe, whenever you are speaking about dipole moment, always remember the negative charge will try to drag the electron. I've been telling that, isn't it? So the dipole moment you always show in this way, an arrow with a line. What does that mean? The charge travels from the positive charge to the negative charge, right? It's going, because the negative charge is pulling, so this is from the positive to the negative. It's going in this direction. Okay, now just see here in this particular case, carbon, hydrogen, 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 hydrogen. Just see 1, 2, 3 and 4. Right. In this particular case, this and this pull is cancelled. This and this pull is cancelled. So mu is 0. Okay. Now in CCl4, CCl, Cl, Cl and Cl. What is the pull? How is the direction? It is from towards the negative charge. It is towards the negative charge. Here it is towards the negative charge. Here it is towards the negative charge. Remember. So this pull and this pull is cancelled. This pull and this pull is cancelled. So here mu is equal to 0. Correct? Because of the shape of the molecule, isn't it? Because of the shape or the geometry of the molecule, it's getting 0. Now let us see water. Now what do we remember? When we done hybridization, it has a bent structure. Water, oxygen here and hydrogen here. This is partial positive, this is negative, this is positive. How is the direction now? It is towards oxygen. This is pulling the electron in this direction. This is also pulling the electron in this direction. Finally, it is in this direction. Correct? So what happened? There is an existence of dipole moment in water molecule. So here it has become 0 because of the shape of the molecule. So I say for a dipole to exist, it should be polar in nature. Correct? The molecule should be polar in nature, and the electronegativity, there should be certain amount of electronegativity difference. Then only higher the electronegativity difference, higher will be the charge. If there is no electronegativity difference, look here, this is 4, this is 2.2, this is 2.2, this is 2.8, very less difference. So if the electronegativity difference is there, then only it will show electronegativity. Now the geometry or the shape of the molecule is very important. Why? If it is arranged like this, they get cancelled and finally will not have dipole. So for a dipole, geometry is very, very important, right? Remember that. Fine. So apart from this, we have learned what is dipole, then we have written the units, then we said what are the conditions. Now let us see how is this dipole, right, applicable. Means what are the applications of the dipole. Then we'll do a question on this, right? So write the heading, applications of dipole moment. So I just now told you, basically, because of this dipole moment, I can easily differentiate. So I'm writing applications of dipole moment. Yes. So what are the applications? Means what are the uses? Because of this dipole, I can easily divide or classify molecules into polar molecules. I can classify them into non-polar molecules, and I can also show whether the bond is non-polar bond or not. Okay. For example, just now we did, right? What are polar molecules? Just now I said difference in electronegativity, like your HC, HF, HCl, HBr, right? HI, difference in electronegativity. Polar molecules, because the electronegativity difference is more, they are showing 2 dipoles. If I speak about non-polar molecules, just like your carbon dioxide, right? Because why? Carbon dioxide, both the sides carbon dioxide here and here. Look here, this and this gets cancelled. This direction and this direction, it gets cancelled. So non-polar molecule, no charge. Yes, methane, just now I showed you. Methane also got cancelled. What else? CCl4 also got cancelled. 0. Right. If I speak about further, like when I'll do one more example, like BF3 and ammonia, I'll show you that also. Right. In non-polar bond, non-polar bonds is like basically hydrogen is a non-polar bond, right? Okay, polar, can I add water? Yes, water is a polar solvent, right? Oxygen as a non-polar bond, Cl2 as a non-polar bond, like the molecules where you two elements combine together, two atoms combine together. So such molecules, but such, because of this dipole moment, I'm able to classify the molecules into polar, non-polar, whether they have non-polar bond or not, right? This is one criteria. Second criteria, based on this, based on the dipole moment, I can also justify, as I told earlier, I can also justify or tell the shape of the molecule or geometry of the molecule. So geometry can be predicted, isn't it? That is what I said, can be predicted. As I said, methane, mu is 0, so it has certain amount of, it means geometry is that what a molecule, it is showing certain amount of mu, so it is bent structure. So like that I can easily predict the shape or geometry of the molecule. So I'll meet you again with one more question on ammonia and BF3. Thank you for watching. Yeah, hello students. So let us come back and do one more concept in your chemical bonding chapter, that is resonance. Yes. So when I speak about this term resonance, okay, yes, let us first go with an example, then let us try to write a definition for resonance. So first let us write the example. Now if I have an ozone molecule with me and I have a carbon dioxide molecule with me, okay, fine, let's see. Now, ozone molecule, basically, if I just go into the structure, they are aligned in this way, right? So, I'll draw the Lewis dot structure directly. One oxygen here, one oxygen here, and one more oxygen here. We very well know oxygen always forms double bonds on one side and single bonds on the other side. Yes. So, 1, 2, 3, 4 double bond, and 1 and 2. Yes. Fine. So apart from this, 1, 2, 3, 4, 5, 6, 7, 8. This is done. Now for this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. This is done. 1 and 2, 3, 4, 5, 6, 7, 8. Correct? Yes. Now this is your Lewis dot structure for ozone. Let us write for carbon dioxide. Now carbon dioxide, we very well know it has double bonds on both the sides. It is so 1, 2, 3, 4 oxygen, 1, 2, 3, 4 oxygen. Correct? Now let us write for oxygen 1, 2, 3, 4, 5, 6, 7, 8. Here 4, 5, 6, 7, 8. This is done. Now from the Lewis dot structure, when I am trying to draw the actual bonds, how does ozone look like? Ozone double bonds on one side and single bond on one side. Correct? Now carbon dioxide, it looks like this: C double bond O, C double bond O. Now observe carefully. Here in ozone, but always remember, triple bonds are shorter than double bonds, which are shorter than single bonds. Remember, this logic is easy. Once again, triple bonds are shorter than double bonds, are shorter than single bonds. Yes. So now I said double bonds are shorter than single bonds. Now when this was measured, when the bond length was measured, the bond length was almost 121 picometer. Here single bonds are, I said, longer, so it was almost 148 picometer when this was measured. Yes, fine. Now here, when this was measured, carbon and oxygen, normally if I see double bond, carbon and oxygen double bond is almost around 121 picometer, and carbon triple bond, if I take, it is almost 110 picometer. As I said, this should be, triple bond should be lesser, so it is 110 picometer. But now when I see carbon and oxygen double bond here in carbon dioxide, it was around 115 picometer. Okay, now see the difference. Here you have double bond difference, here you have single bond. Here also again there is a variation in bond length. So for that, for such structures, a concept of resonance was introduced. So what is this resonance? Now what happens, now this is your actual structure, right? So this structure always is in, now I'll take out this, now I need this board, okay. Now this structure, when I observe the structure, this structure basically always exists. Now always, when you have a pi bond, we always know there is delocalization, right? Shifting of pi bonds. While to attain stability, right? Now this double bond will shift here. Then how does this look? Oxygen, single. Now this is double bond, this becomes single bond. Now this is your double bond, becomes a single bond. Just opposite, double, single, single, double. So what is single bond now? 148 picometer, and here this is 121 picometer. Now when I take these two, now this is one structure, this is one structure. These two structures are called canonical structures. Observe, canonical structures. Canonical structures. Now when I mix up two canonical structures, I get a new structure called resonance hybrid. So this is called resonance hybrid. Observe carefully, resonance hybrid. So how does this resonance hybrid look? Combination of both, correct? Combination of both. So how do I get oxygen? This is here, and the pair or the electron pair, we call it as the hybrid. We represent it by dotted lines like this. The electron or resonance hybrid. Fine. So this resonance hybrid, when observed, it has a bond length or in between these two that was almost 128 picometer. So this resonance hybrid basically explains, or it is obtained from the combination of two canonical structures. So I'll write for that, then we'll write the definition or the concept of resonance. So let me write for this. How does this look now? In this Lewis dot structure, suppose when I write this carbon dioxide, so observe carefully. Now I'm taking the same molecule. Now I'm showing the resonance structures of canonical structures. I have to make double arrow for canonical structures. Now see, carbon in the center, one bond will shift here. So 1, 2, 3. Okay. Yes. 1, 2, 3. What did I do? I shifted this bond here. Exactly this electron I took it here, and this electron I just shifted this here. So I've got 3 electrons here. So oxygen. Okay. Now what happened here? We have only one set. This is one oxygen. So let us write the electrons, fill the electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now let us see here. 1, 2, 3, 4, 5, 6, 7 and 8. Now what happened to this oxygen? It has got excess electrons. I mean, it has not excess, I should say. Compared to this, it has more electrons. Yes. So this attains a negative charge and this becomes a positive charge. Yeah. Now when I write one more canonical structure, when I write a resonance, one more canonical structure, this will shift here. So this becomes C. So what should I do now? Instead of writing this here, I'll write these two are canonical structures. Yes. Now what happened? This oxygen. Now here you have this bond. Now shift this here. This carbon, 1, 2, 3, 1, 2, 3 bonds. Correct. Now you have your oxygen here. Now on the other side, 1 and 2, you have your oxygen. Now count. This has 3. So 3 plus 3 6, and you have 2 electrons. On the other side it has 2, 3, 4, 5, 6, 7, 8. So this has lesser electrons, so this becomes positive, this becomes negative. Yes, observe. Now I have to draw a resonance hybrid of that, isn't it? So this becomes carbon, oxygen, oxygen, and this is your resonance hybrid of this. So what did I say? This had a bond length of how much? Almost 115 picometer. Right? Now observe carefully. How am I defining this thing? According to the concept of resonance, observe, when a single structure can't represent a geometry of a molecule, okay, when a single structure can't represent, so let us write that. If I have, yeah, I'm writing the concept when a single structure cannot or can't represent a geometry of a molecule geometry of a molecule, then what do we go? We consider canonical structures. So canonical structures, what is it important, like what do they have? We consider canonical structures. So this canonical structures, so these canonical structures, what do they have? What similarity they have? They have same bonding. When I compare this one, same thing, they have same bonding and non-bonding electrons, both are same, which are bonding, and if they have any lone pairs, bonding and non-bonding electrons will be the same. Positions of atomic nuclei are the same, because both, look here, nothing, we just shifted, it's the same thing, but we shifted the pi electrons and sigma bond. So positions of atomic nuclei is the same, non-bonding electrons is the same. So because of this canonical structures, this one, we consider. Now what happened now? I took this molecule, I wrote the canonical structures. Now we start considering this canonical structure as a basic structure. Now this becomes the geometry of the molecule, right? Now because of this, what is the use concept? Because of attaining this, or because of writing this canonical structures, the molecule tries to attain stability. This is the main concept, attaining stability. What happened? Why? When I observe, or when I check the energies of this molecule formation, the energy of the resonance hybrid was very less. Energy was very less. We always know if the system has lesser energy or lesser disorderness, the particular system is very stable. Always the system tries to prefer the lesser energy or lesser disorderness. If the disorderness is very less, the energy or the system is more stable. So because of this resonance, if your teacher is asking you what is the use, or what the concept of resonance, what is that leading to, then you can write, because of this resonance, the system reaches or attains certain amount of stability, because the system energy has gone, it is too low, it is low, and finally it has reached as a point where it is completely stable enough. It is not disordered, it is stable. So once again, resonance concept basically explains the concept of canonical structures. Why do we take canonical structures? So that the system comes to a state of stability. More number of resonating structures, more is the stability. Remember that. So to attain that concept of resonance, or to attain that concept of stability, they show resonance. So the concept is explained using canonical structures. So please note this. If you have any doubt, please let us know in the comment section. Good evening students, welcome to one more session of your WOC, that is World of Chemistry. The students who have joined new to this channel and the students who are watching, who are there with me since 3 years, right, good evening again. So here, as I have to tell you, compared to the last year students, this batch students are very lucky. If I have to tell you, I understand, you have that tension when which exam will be there or not there. Leave that all uncertainty. Feel happy. You're getting extra days for preparing. Yes, students. So we as educators, for making one particular video, we really put in 100% effort. So we as educators, we expect you all to watch the video, share it, and if it reaches more and more number of students, as an educator, we feel happy. Right. So as I said, I have started with the inorganic series where I did D and F block questions, coordination compound questions. I did, ionic radii, ionization enthalpy, atomic radii, mock tests also. Like that, inorganic series is going in full swing. Right. So, and next important, as we know, in inorganic, different chapters are there, very important for your exam. That is chemical bonding, SPDF trends, equilibrium, electrochemistry and physical chemistry. Like that, all these chapters, they, compulsory questions will be given either based on trends or based on the, increasing and decreasing order, something like that. And next, they'll be asking you to solve the question. Time is less. But for that, you need some trick to solve the question, correct, isn't it? So whenever I put a thumbnail or when I put a title, trick for coordination compound, compulsory the video will have certain amount of tricks for you all. So please watch the complete video. Right. So today the topic which I have chosen, the important chapter, that is your chemical bonding. So chemical bonding is a chapter. As I said, in chemical bonding, I have already taught 100% of the theory which is kept in the playlist. Right. So everything I have done in chemical bonding and kept number wise. Today I am going to teach you the tricks for solving the important questions based on covalent character. I'll be doing the covalent character questions, how to solve it. I'll be doing questions based how to solve ionic character questions, bond parameters, that is bond length questions, bond order questions, bond angle questions, polarizing power questions. I'll be also doing question based on hybridization. I'll be doing question based on your dipole moment. I'll be doing question based on hydrogen bonding. Right. So like this, all the concepts of your Vesper theory, VBT theory based on your chemical bonding, I'll be first giving you the trick for each concept. So what possible options or what trick you need to remember in that concept I'll explain. After that, whatever are the relevant questions, so question will be given and an answer solved away will be done. So for all these, little bit the video duration will be long, but after doing all these, after understanding the trick and solving the questions, you will have a clear idea, okay, when stability question is given, I have to apply this trick. When polarizing power question is given, I have to apply that trick. Right. So let us come and start with the first concept. Covalent character, increasing order, decreasing order, what it is, let us understand. Trick as well as question and answer from my side. Let's start the video. Right, now let us start with the first concept, that is covalent character. Here I have taken 3 different examples which you will be asked quite frequently. Right, if you understand the concept here, you can apply this concept in any equation which is given based on covalent character. Right, so this is basic Fajan's rule which I am using it. Let's see. What should you remember? Whenever covalent character question is given to you, 3 concepts you need to remember. What is that? Remember, higher the charge of cation, okay, higher the charge of cation. So instead of writing the sentence, let me put like this in this arrow, higher the charge of cation, okay. Covalent nature, covalent character or covalent nature character will be more. So the first one is over. So charge is higher means covalent character is more. Right. Next, what should I remember according to the Fajan's rule? The next one, the smaller the cation. So cation is smaller. If the cation is smaller, anion obviously, that is your larger anion. Smaller cation, larger anion. This is also over. If the cation is smaller, simple thing, you need to remember the covalent character will be more. Done. Let me draw this line. If the anion is larger, again the covalent character will be more. Remember, simple, isn't it? Smaller cation, larger anion. We know that covalent character more, covalent character more. So here also charge is more, cation charge is more, covalent character is more. So simple. What should I apply in this? Now I'll remember all these and go to the exam and apply the same. If the charge of the cation is larger, we said. Now we have in all these 3 salts, we have cation different, cation different. What is similar? Anion is similar. For me, that's not the problem. Now I have to see the charge. If I take the sodium chloride, this is Na plus. This is magnesium plus 2. Aluminium is aluminium plus 3. Simple as that. So here I said if the charge of the cation is more, covalent character is more. Now simple. Charge of the cation is this, which will be more covalent. Aluminium chloride is more covalent compared to Na. Let us rewrite. NaCl, if I to say this is ionic in nature, less magnesium chloride intermediate, less aluminum chloride AlCl3 covalent in nature. Simple, isn't it? I have applied the first rule to this. So NaCl is an ionic compound, aluminum chloride is a covalent compound compared to NaCl. Okay, right. Now when I take the next one, let us apply this concept here. We said smaller the cation, covalent character should be more. Smaller the cation. Let us check. Here all anions are similar, only is cation different. So the cation here is barium, here the cation here is magnesium, cation here is calcium, cation here is beryllium. So what should I remember? Cation should be smaller. Among all, which one is a smaller cation? Beryllium. So beryllium comes here. So beryllium is what? It is more covalent in nature. So beryllium is covalent character is highest maximum. If I have to see which is the largest cation among this, beryllium, magnesium, calcium, barium. So barium comes here, barium chloride. So barium chloride is ionic in nature according to this, because the cation is larger. I said if it is smaller cation, it will be covalent. Larger cation, it's ionic rather than other way round. Right. The next one, if I have to compare magnesium and calcium. So this is larger. Next one is which one? Calcium chloride. Next one is which one? Magnesium chloride. And next one is beryllium chloride. So beryllium chloride is covalent in nature. Barium chloride is ionic in nature. That's done. Let us compare this. We said anion should be larger, covalent character will be maximum. Now we will see. Here cation, all cations are similar. Nothing to bother. For us in the exam, if they give anions are, we have to see this. Now among these, calcium fluoride is a smaller anion. Calcium iodide is a larger anion. So I said anion should be larger. Let us write the order. Calcium iodide is more covalent. What is the reason? Just now we have written anion larger. Among all these, fluorine, chlorine, bromine, iodine. Iodine is a larger, so more covalent character. Which will be more ionic? As I said, calcium fluoride will be ionic in nature. Why? According to Fajan's rule, anion is larger means it is covalent. Anion is smaller means it is ionic in nature. Now let us rearrange. What is left? Fluoride is over, iodide is over, then comes calcium chloride, then comes calcium bromide. So if I have to write in this way, lesser, lesser, lesser in this direction, isn't it? So this is clear, students. Simple concept, nothing to get confused. Remember this, apply it. So whenever covalent character questions are given to me, I have to remember charge should be higher of the cation, size should be smaller for the cation, anion size should be larger, then only covalent character will be more. Now let us come and do the next important question, very interesting, about the next example in your chemical bonding. Right, so let us come and do the next topic of your chemical bonding, that is your bond length and bond angle. That here they have given me a question, arrange the following in the increasing order of their bond length and bond angle. What should I remember here? The basic concept you should remember is bond order is inversely related to your bond length. Done. Next concept, bond length is inversely related to the bond angle. If this increases, this decreases. If this increases, this decreases. Let's see whether I am correct or not. Here they have given me this question. As soon as this is given, just let us write structure quickly. NO2, this is your plus. What is the shape of the molecule? It is linear in shape. Whenever it is linear, the bond angle is compulsory 180 degrees. Yes. Now when I take the second one, NO2 in this way, oxygen minus. What is the shape of this molecule? This is a bent molecule. Done. The shape of this is bent. So this the bond angle is 132 degree. In this case, NO3 minus oxygen 1, double bond oxygen, 3 oxygens, done. Here the shape of the molecule is trigonal planar. Trigonal planar. The bond angle is 120 degrees. Done. Now Say next, bond angle is over. Now I have to write bond order. Basically, I'll teach you a small trick on bond order in the next 5 minutes. So as of now, I'm directly writing the bond order. For NO2 plus is 2. This is 1.5. This is 1.33. This is over. Now I have to apply it in the question. How should I do? As I said, see, for which one is the bond order more? Bond order is 2, 1.5, 1.33. Now what did we say? If the bond order is more, bond length will be less. Now let us answer this question. Bond length order is, according to the increasing order, the whichever has bond order more, its bond length is less. Bond order more, bond length is less. Let us write. So NO2 plus will have less, bond length will be lesser compared to next one NO2 minus compared to NO3 minus. This is done, students. This is over. Simple. Now I have, this is over. Now I need to write in terms of bond angle. Now what did we say? Simple. Bond angle and bond length are inversely related. You can only check. See here, bond angle is 180 degrees. Right? So here 132, 120. Now when I take NO2 plus, let us write this here directly. It is 180 degree bond angle. Next comes 132 degree bond angle. This is 120 degree bond angle. Now you only say whether it is reverse or not. See here, angle and length are reversed in this one. The one which has lesser bond length has more bond angle. The one which has lesser bond length has more bond angle. Correct only, no? So how should I write the order in this way? Bond angle increasing order, the maximum would be, that means NO2 plus will have more bond angle greater. The minimum will be NO3 minus. So NO3 minus is less than NO2 minus, which is less than NO2 plus. This is clear, simple. This thing I have applied in this question. That's all. Let us check, recheck. This one, the bond length, compared to this, from the bond order I got more bond order, less bond length, more bond angle. Simple as that. Right, students, let us come and do the next concept, that is your hydrogen bonding. So what should I remember in this? Let's see. Remember hydrogen bond strength. So they may ask you in this question, they either ask you, okay, let us not write the order first only, let us see whether we can justify it or not. From here I need to find which is having more hydrogen bond strength, right? So remember, hydrogen bond strength, if I have to see, it's directly related to the electronegativity value. If the electronegativity value is more, hydrogen bond strength also will be more. And it is inversely related to the size of an atom. Okay, how can I apply this concept in this? Let's see. When I have to see among all these, hydrogen electronegativity value is 2.1, fluorine is 4. Okay, hydrogen again is 2.1, oxygen is 3.5. Here when I take hydrogen is 2.1, nitrogen is 3.2. Hydrogen is 2.1 and chlorine is 3. Now, among all these, fluorine has the highest electronegativity and chlorine has the least electronegativity. So, the bond strength, this will be maximum because both are directly related. This also maximum, this also more. Simple, isn't it? So, I have applied that concept. So, in the exam, as you see, directly if they give you, you can apply the concept and solve the or put the tick in the correct option. Right. So let us come and do the next concept based on the stability question. Right. So here, remember, such question is given to you. They've asked you to arrange according to the or increasing order of their stability or decreasing order. No problem. Let us. It's okay. Anything they give, concept you need to understand. Here, suppose in this question, I need to understand based on their electronegativity. Why? Because whenever you have stability questions, you should compulsory remember most electronegative element. Okay, if the electronegative element is more, means the electronegativity value is maximum, the stability will be also maximum. Remember, stability is maximum. If the electronegativity is maximum, stability maximum. So if I have to see among all these which has maximum electronegativity, fluorine. So fluorine has the most, it is most stable if I have to say according to this concept. Done. Among everything which is least stable, so let us write this one, stable, since electronegativity is high, that is 4 is electronegativity. Done. Let us come back. Here among all these, this has carbon has least electronegative, so least electronegative atom, that is carbon, so more, that is unstable in nature, right? So it is unstable and that is stable, right? When I have to compare both these two, next comes nitrogen in the picture, less stable. After that comes, compared to these, fluorine is over, least is next, oxygen, because of its electronegativity. Now see, least electronegativity, then next comes nitrogen electronegativity, then next comes oxygen, then fluorine is maximum. So what is the concept? Whosever electronegativity is higher, the stability of the negative ion will be more. Now, one more concept you can remember. Whenever there are, there is no resonating structures, let us assume like this. Suppose you have something like carbon, double bond O. There is one more like this, plus, and your carbon, this is minus in this case. So if I have to compare these two stabilities, simple, the one which that is resonating but which doesn't have any charge is more stable. Compared to this, the one which doesn't have charge is more stable compared to one which has charge, right? So this is how you need to remember. So whenever stability questions are given, understand or remember this concept, go and check the electronegativity value and finish off the answer. Right, now let us come and do one more question based on polarizing power. So on polarizing power question is given. Here there is one certain question given with charges. Let us analyze how to do. So whenever this sort of question, arrange the following or take the correct order of the polarizing power, such questions are given to you. Remember again the same Valence rule I am applying. Smaller the cation, right? One concept. Higher the charge of, higher the charge, that is a positive charge which I am talking about on these cations, right? Higher will be the polarizing power. Higher will be the polarizing power, right? So now among these, which is the correct order if I have to see? So which is the maximum charge? Aluminium. So aluminium, wherever aluminium is there, that is where you need to see. So higher is a charge, higher is a polarizing power, I said. So among all these, aluminium is there in option A and aluminium is there in option D also. Right. Next comes here I compare magnesium same, potassium cesium. Now we very well know cesium, francium, all these are radioactive materials. They are not going to react. That is why when I have to speak which is more polarizing, this option is the correct option because of this radioactive material. So here this comes cesium, then come potassium lesser, magnesium lesser, aluminium is maximum. So please try to apply this concept in this. So the first option, aluminium will be having more polarizing power compared to cesium. Right, now let us come and do one more question based on the concept of bond order. Right, so basically bond order, I'll give you a trick here, just remember. So normally if I have to see the definition of this one, bond order is nothing but total number of atoms by, in the particular structure, by total number of resonating structures. Okay, total number of resonating structures. Number of resonating structures. Okay, so here in the exam, it's very difficult for you to keep checking, drawing the structures and everything. So one trick for you all, remember. So I'll erase this and just see, I'll give you one important thing. What is that? Simple. Whichever structure is given to you, you need to calculate the bond order. Follow this step. Step number 1. That is, first you calculate the total number of electrons. So to calculate the total number of electrons quickly, you can know atomic number. If you know number of electrons, you can easily predict. After that, quickly what you can do, you after getting the total number of electrons, you're going to subtract that from 14. Subtract it from 14. Done. So once you get that answer, you're going to use this formula 3 minus 0.5 into n. So the subtracted number you will be writing in this n. Let us do what I tried to tell you. For the first one, it is n minus 2, 2. What is the total number of electrons? Nitrogen atomic number 7. So 7 is the number of electrons. 7 into 2, 14. So there are 2 electrons extra. So plus 2, it comes to 16. First step is over. In the second step, you subtract it from 14. So 14 minus 16. So it becomes minus 2. Then you are going to the third step. 3 minus 0.5 into minus 2. So according to the board mass, you solve this. You get an answer of N2 minus order is, if you take 2.5, okay. So it's nothing but 2. Yes. Done. So same procedure. If I have to do for the next one, I'll erase this, and the same thing for next one, that is N2 minus, same thing, 7 into 2, 14, minus 1 means add 1 electron, 15, 14 minus 15, apply it in the third step, 3 minus 0.5 into 1. So this comes to 2.5. If I have to do the next one for nitrogen, number of electrons for 1 nitrogen 7 electrons, 2 nitrogen 14 electrons. So 14 minus 14 is 0. I'll apply in the third formula 3 minus 0.5 into 0. What is left out? Nitrogen, the bond order is 3. Simple, right? So I have got 2.5, I have got 2, and I have got 3. Right, simple, isn't it? So what did we get? We have got 2.5, we have got 2, we have got 2.5, we have got 3. So the correct order, they said, which of among the following is the correct increasing order, the bond order? This is correct. The first option is the correct option, right? So this is how you're going to calculate. Simple, nothing. Again, I'll just repeat it. Whatever is the total number of electrons, write it. So for 1 nitrogen, it is 7. For 2 nitrogens, it is 7 into 2, 14. Done. After that, you're going to subtract from the number 14. I get 0. Then I'm going to substitute with 3 minus 0.5, n, that is n value is 0. Finally, I have got 3. The bond order we very well know, no? Nitrogen, triple bond n. This is a bond order. So this is how you need to calculate and quickly put a tick to the right answer. Now we will take one more example, that is with oxygen, and it's easy, simple. Use the same bond order formula for that, apply it and tick the correct answer. But there, oxygen, it can be oxygen atom, O minus 2. Let us see the example and do the correct or tick the correct option. Right, now let us see among all these given oxygen atoms, what is the order? Some simple logic, as I said, use this formula and we can directly write the order. So I'll show you one example. Oxygen, number of atoms are 16, correct? Done. There is no valency now, no charge on this. Directly take it and go to the next step, subtract it and you'll get minus 2. This is fine. Then apply it in the third step. This is 3 minus 0.5. Number of electrons is this is minus 2. So when you solve this, you get the oxygen valency or the bond order is 2. That's why oxygen double bond O. Like that, when I solve everything, we get the bond orders like this. Oxygen is 2. O, the second option is 2.5. The third is 1.5 and the fourth is 1. Now simple, same thing I have applied in everything. If I have to write the order, the correct increasing order according to this question, the highest is which one? The increasing order means the first thing should be the less, the last one should be the maximum. So here 4 is minimum. Okay, no problem. So 2 is there, 2, 2.5, 1.5 and this one. So the least one, if I have to write, 1 is least. Okay, so 4 is less than. Next come to 3. 3 is less than 2. 2 is less, okay. 3 is less than 2. 3 is less than 1. I'm sorry. 3 is less than 1, less than 2. Let us see. Now the fourth one is 1, that is O2 minus. Let us write O2 minus. The bond order is 1. It is lesser than 3, that is O2 minus. Done. Which is further less than oxygen, which is further less than O2 plus. This is the order. Simple, isn't it? Use the bond order technique and try to solve this question. Right, now let us come and do or solve one more question based on your bond angle. So what should you remember in bond angle? Let's see. So always remember in terms of hybridization, if you speak, the bond angle in terms of hybridization, right? So Sp will be greater than Sp2, will be greater than Sp3, greater than Sp3D. In that way it carries on, correct? Right. The next thing or next concept which you should remember is, as the number of lone pair increases, the bond angle also increases. Remember that. Next clue which you should remember is, if the lone pairs are 0, means there is no lone pair in the structure, bond angle will be same. Means the bond angle will be same. There's not change in that. Let us see in this question. Right. So here, and next important thing, fourth important thing which you should remember is, see, suppose there is one atom like this. In this way you have atoms, so B, C, D, right? This is the central atom, these are the side atoms. Now I'm going to give the concept in this way. Just see, if the central atom, this one is different, if the central atom is different, I'm giving this, and side atoms, this, and the side atoms are same or side atoms are similar, then what will happen? Remember this thing, when the central atom is different and the side atoms are similar, your bond angle is inversely related to the size of central atom. Next concept which you should remember is, I'm writing the fifth concept here in the same way. Here we have written central atom different. Now I'm writing, if the central atom is same and the side atoms whatever are attached, side atoms are different, then what will happen? Remember, your bond angle is directly related to the size of side atoms. All these concepts will cover all the bond angle questions. So with this concept, I think you can almost rather all the 5 options you can use it for solving the bond angle question. Right. So here let us solve this now. Here I don't have any information. Only thing I have is, on these particular thing there is charge. Now as soon as that thing is given, which one to apply hybridization I don't know. Like I think the second concept, that is lone pair, I can apply. I'll take that and draw the structure NH2 minus. Draw the structure. Nitrogen is here, 1 hydrogen on this side, 1 hydrogen. How many are over? 1, 2, 3, 4, 5, 6, 7, 8. And minus is already there. Next structure, now how many lone pairs are there? There are 2 lone pairs. 1 and 2. If I have to take the next ammonia structure, ammonia, N, hydrogen, 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 count 1, 2, 3, 4, 5, 6, 7, 8. How many lone pairs are there? 1 lone pair is there. When I take the last one, that is NH4 plus, let me draw the structure. Nitrogen, hydrogen, 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 and one more hydrogen and plus. How many lone pairs are there? 0 lone pairs. Simple. Come back to the option now. Just see. So here NH2. Now they said which is correct in this. Okay. NH2 minus is greater. NH2 minus is greater. Lone pair. This option is correct here. First option. Because remaining all are wrong. NH2 is greater. 2 lone pairs. Done. It is greater than ammonia. Ammonia 1 lone pair. That is also correct. Then NH4 plus is 0. That's also correct. So the correct option is this one. Isn't it? So what did we do? We have solved it on basis of more number of lone pairs, more is the bond angle. So you can use options 1, 2, 3, 4, 5 for different bond angle questions. Now let us come and do a question based on dipole moment. Right, now let us come and see the next concept, that is question based on dipole moment. So I did a video what actually is dipole moment, what actually is mu, what is d by, what are the different values you need to remember, how do we calculate magnetic moment, how do we calculate dipole moment, like that. I did everything and kept in the playlist. Please check that video, dipole moment. Right, now here we will see what are the techniques or trick what I have to remember during exam. Right, so basically dipole moment, when I say remember, dipole moment is directly related or directly proportional to the electronegativity difference. If the electronegativity difference is more, automatically dipole moment will also be more in that particular molecule. Done. The next concept which you should remember is the dipole moment is directly, or if I have to say this one, the dipole moment in terms of your lone pair. So if the number of lone pairs are more, okay, if the number of so if you see to draw the structure and see, if the number of lone pairs are more, then also dipole will be more. So directly related. Done. One more concept is your dipole moment is inversely related to 1 by theta. See, when you have an substitution, the ortho position, para position, meta position, that angle what is there, that is inversely related to dipole moment. If this increases, this decreases. Done. Right. So based on this concept of this particular basic trick, let us apply this in the question and see. Here they have given me arrange in order of increasing dipole moment. Done. So here important, first thing, the least one should come first and the maximum more dipole moment should come in the last. Done. Here among all these, what are you observing? Highly electronegative element, fluorine. See here, more is the electronegativity difference. So this is 2.1 is this is 4 is electronegativity. Here hydrogen is 2.1. Correct? We have written this one. This electronegative values also. Just see, among all these, among oxygen, sulfur and fluorine, fluorine is the highest electronegative atom. Correct? Right. So among this, as I said, as electronegativity difference increases, dipole moment also increases. Done. So the first one is BF3. Done. After that is, what is the next one which comes? Among sulfur and oxygen, which has more electronegativity? This is. Then again after this comes oxygen. Simple, isn't it? So BF3 is, okay, ma'am, why you're saying in terms of BF3, I'm getting confused. One more thing also I'll tell you. Here in BF3, the molecule is linear or the molecule is symmetrical in nature. Exactly, the BF3 molecule is symmetrical, right? Okay, so here in terms of symmetry, if I see, the structure is symmetrical, then also dipole moment is 0. What? The one more concept which you should remember is the structures which are linear in nature, the structures which are tetrahedral in nature, the structures which are trigonal in nature. Okay, the molecular structures trigonal in nature. So remember, for all these, the dipole moment would be 0. But there is certain exception like SF6, which has, distotal tetrahedral structure, distotal structure. Because of that, it has permanent dipole. That is an exception. Next important thing, structures which are angular in nature. structures which are seesaw in nature. Such structures they will possess certain value of dipole moment. Remember that. Okay. Now I am applying this concept here. So according to the electronegativity value, fine. This is almost 2.2. This is more than that, 3.3 or something. Now according to this concept, BF3 is a symmetrical molecule. It is a symmetrical molecule. So for the symmetrical molecule, if I have to say the symmetrical molecule, what happens? The dipole moment, as I said, is 0. So the dipole for this, according to this, is lesser. Next comes sulfur and oxygen. This is compared to this, the electronegativity is more. The difference is more. So this is lesser than this. So here the electronegativity difference of oxygen and hydrogen is more compared to sulfur and hydrogen. That is why directly related, the correct order given, or the correct order is this. Let us come into one more question. Right, now let us solve this question based on this concept. Here they've asked me to arrange according to their decreasing order of the dipole moment. Means they've asked me which is the maximum dipole, which has the maximum dipole. Let's see. I said the electronegativity difference more means dipole also would be maximum. Here are the electronegative values. Just see. Now as we know, hydrogen is how much? 2.1. Okay. Now here carbon, because this bond here it forms in this way, isn't it? Carbon, 3 hydrogens are there, and you have iodine also, like this. So I am finding or writing the difference between carbon and iodine. So here carbon is 2.5 and iodine is 2.2. Here carbon is 2.5, bromine is 2.8. Here carbon is 2.5 and fluorine is 4. Here carbon is 2.5 and chlorine is 2.9. Whose electronegativity difference is more? Carbon and fluorine. So this will be maximum. Then comes CH3Cl, less. Then comes CH3Br, less. Then comes CH3I, less. Simple, isn't it? See the difference? Carbon also 2.5, this is 2.2. So larger the electronegativity difference, more would be the dipole moment. So this will be more dipole moment compared to CH3I. Here less dipole. We can speak in terms of bond length also. Shorter the bond length, longer the bond length also. Let's see 2 more questions on dipole moment. Right, now let us again do 2 more questions based on this concept. Here what do they give us? Which molecule has 0 dipole moment? Okay, so here I think in the last question I have applied this. Now let us see one more which I can apply the structure. Right, so here we said linear, tetrahedral and trigonal will have 0 dipole moment. Right, exceptions are still there. Now among all these molecules, which is a molecule which has linear structure? Carbon dioxide. So carbon dioxide is a molecule which have 0 dipole. Simple. Let us come and see here. Which molecule has largest dipole? Again the same thing. When they say largest dipole, your concept should directly go into this electronegativity difference. So here compared to chlorine, iodine, bromine and fluorine, the electronegativity or the electronegativity value of fluorine is high. So the difference would be here 2.1 and 4. So the difference is maximum. That is why HF has the largest dipole moment based on this concept. Right. So these are the different concepts, students. So I have covered concept on stability. I have covered concept on polarizing power, bond length, bond angle, bond order, covalent character, ionic character, dipole moment, lot and lot. So like this, I think the trick and the questions which I have given you will really help you out. One important thing, remember students, here for making a particular video, we as educators, it takes a lot for us to do. It is not simply we just upload, copy paste and give it to you. For us, we want every student to be benefited. So we put lot of efforts. As an educator, I believe more than an educator, the students have to put more I think 100 times more effort, because it is your future, isn't it? So please watch the complete video. I'll be meeting you next with a very important video, that is your DNA block trends and exceptions also. Wait for my next video. I think this is clear for you all. I request you to share to more and more friends so that it will be very beneficial for your GE, CBSE as well as NEET examinations. So study well, stay happy.